Good morning. This is Ranjan again here. Today we have the A2 keynote presentation session 2 here in this room right now. And we have 3 keynote presentation. I request Professor Scott Bunn to chair the session and Mr. Lilanath Rimal for the co-chair. We have rapporteurs Dev Kumar Sambo and Mr. Ishur Thapa.
The first speaker today, the first keynote speaker, has been a friend for 2 years. And it's a wonderful chance to introduce to you Dr. Gopal Dhawan. He was past president of the India IAEG National Group. And we were in New Delhi 2 years ago, got a chance to meet him there. He has a long and distinguished career. And he was... For 32 years, he worked for the National Hydropower Corporation in India, which is huge. And then for the last 5 years, he has been chair of the Mineral Exploration Corporation. So very, very involved in energy and minerals during that time. He is also chair of the president of the India Geological Congress, which is coming up. And then in 2 years, we have the International Geological Congress coming to New Delhi. And so IAEG will be having a meeting at that time, and he just happens to be another chair of that one, so he's very involved in that. And I also think that it's very important to say something about your family. His lovely wife is here. He has 2 children and 1 grandchild. Very, very important. How about a round of applause and welcoming Dr. Gopal to come and talk.
Nepal is a very important place in my life. It was here where I started my career as an engineering geologist. And I was working for a small hydropower project which is about 70 kilometers from Kathmandu. The name is Devighat project. It was commissioned in 1983 and working very well, supplying power to Kathmandu now. And for this, I must thank the organizers of this conference, and particularly my friend, Mr. Dahal, Dr. Dahal, who encouraged me to come here. Otherwise, I was so hard pressed for time that it was practically not possible to spend 3 days just before your retirement, because there are so many formalities in which were to be done. But somehow I am here, and I am very happy to be here. So now, you see, coming back to the assignment which organizers want me to do, is sharing my experiences, whatever we could do, and particularly, because Himalaya is the storehouse of hydropower for India as well as our all neighboring countries. So the topic I chose is managing geological situations, not problems. Managing geological situations at hydropower projects in the Himalayas. And the slide in the background is of a project named Nimbo in Leh and Ladakh. These are barren hills in Tibetan Himalayas because of very high altitude and weather conditions. These are all devoid of vegetation. Very small vegetation is there. And these are all fragile rocks, sedimentary rocks of Tethys, and we constructed a project here. It was a challenge. I'll address to these issues as I proceed further. I'll briefly introduce the issues and challenges we have faced in several projects, then how we managed them, and I will touch 2 case studies which are very close to my heart. One is the Dhauli Ganga project in Uttarakhand, a hilly state in India, and another one is Kishan Ganga project in Jammu and Kashmir. And what can we do? I mean, still projects, whenever we are going for a new project, every project has a unique problem, which was never anticipated before. So that is a big challenge. So we have to keep on thinking innovatively if we want to construct projects in Himalayas. Well, this is how Himalaya looks on the globe. It's a simple arcuate mountain chain, very prominent feature, a very important mountain chain. In Indian part, it runs for about 2,400 kilometers from west to east, and its width ranges from 400 kilometers to about 150 kilometers in Arunachal Pradesh. Just if you see a bit closer, I mean, when you focus in Himalayas, we have divided this mountain chain in our country for our own convenience of reference, western, central and eastern Himalayas, and we have constructed projects all around. Still, if you go closer, you will find the geology, and you see, these are the thrusted sheets, the thrust slices, resting one over the other. If I try to focus on from south to north, after the Indo-Gangetic plain, we get Shivaliks, then we get lesser Himalayas, then we get higher Himalayas, and the Tethys, the glimpse of this mountain you saw in the first slide, and then the Trans-Himalayan Granite. Each geological sector is separated by normally a thrust fault. The Indo-Gangetic segments are separated by Himalayan frontal fault. Then MBT separates, the main boundary thrust separates Shivaliks and lesser, and main central thrust is in between lesser and higher, and the Tethyan sediments are separated by South Tibetan detachment system. So a little bit of geology, and then you see now you will find the same separation boundaries in between these tectonic zones which I just narrated, and you will find that we had an opportunity of constructing projects in each Himalayan domain, be it Shivaliks, lesser, greater, or even Tethyan. And you will find a number of names here: Dulhasti, Kishanganga, Uri, Salal, Theen, Bhakla, the first major project which came in India and which was the root cause of green revolution in our country. It is situated in Punjab. Then Parvati project, which is under construction and having a lot of problems while application of TBM in Himachal Pradesh. Then Nagpa Jhagri, the longest tunnel ever in India. Then Teesta 5, this also had so many problems, but it is commissioned and doing very well. Most of these are commissioned projects, I would share with you, except Subansiri. And then we had a project in Manipur which is known as Loktak. I mean, this was the project where very huge tunneling problems were encountered, and this was the learning ground of many geologists in our beginning of our career. Then Maneri Bhali, Tapovan Vishnughat, which is still going on, and Chamera 1, which is constructed. It is 540 megawatt project in Himalaya. So you see, what I wish to share with you, and this talk, encompasses almost all kinds of experiences which we had in several parts of Himalayas and several projects. To structure that what kind of problems could have been encountered and what could have been there in the future projects also. It is a presence of paleo channels. Dam foundation problems are very common, but I must say that with good geological exploration and investigation, we were successfully able to assess even before making the technical specifications. Cavity or chimney formation, very common problems in tunnels. Of late, in 2 or 3 projects, we suffered with very high water ingress. For example, Dulhasti and in Parvati, which we are still negotiating. Then daylighting of tunnels in low cover zone. This was my first, you can say, face-to-face with a geological problem in Devi Ghat, which is constructed in Nepal. Although it's a very small project of 14 megawatt, but we had two small tunnels. One was 850 meters long and another was about 700 meters long. In the longer one, after we completed the tunnel and the tunnel came face to face and it was daylighted. It was a DPM tunnel, very conventional. We constructed it very, you can say, with conventional methods and very primitive methods. And after the completion of the excavation work, because both the phases matched very well, there was a jubilation and celebration in the project for about 3 days. And all of us were must. I was also young, and you see, there was a lot of parties going around, and during these 3 days, we did not care to provide support. And the tunnel came down. When after 3 days we went there, we found that you see, all our drilling jumbos and all are buried below the mud. So now, you see, as a geologist, although I justified that rock is poor, but in my heart and with my experiences later on, I said it was not the rock. I think we were weak or we were not. We did not respond to the requirement of the tunnel or this excavation timely. Otherwise, this could have been saved. So this is a very, a situation which was felt here in a local domestic project. And then we had to struggle for about 4 months to once again clear the face. And high stress problems and high temperature problems, all I think are known to each one of us. You see, all through my career, I had always been pondering upon that we club everything into a geological surprise. Is it fair? I mean, are we not doing injustice to geology? I mean, I'm talking about this part of the world, maybe India, Nepal, Bhutan, where we had been very actively working. That you see, there are certain situations which are not known, and they may be very genuine geological surprise because it was not anticipated. But in my own opinion and my own experience, I have seen that all contractual as well as managemental issues are also clubbed under the term of this geological surprise. In my opinion, there is a need to be judicious about this, and the approach should be reasonable. Maybe it will be good if we club it in some name of a geological risk or geological problem, which are more quantifiable rather than geological surprise. To share with you the situations which I had faced, this you can see a shear zone and dam foundation, and I must share with you that we could not anticipate it, and therefore a lot of design changes were required during construction of a project. This is a failure in a search shaft which was in Teesta project, and it was after the construction of the shaft. So certainly there was some misjudgment of the rock and soil properties during design as well as construction. This is a major slope failure in Subansiri project, which is under construction right now. This is around more than 200 meter high rock face. Rocks are very weak in shivalics, but anyway, now the slope has been rehabilitated very, very effectively. This is a wedge failure in Nimbu Basco project in Jammu and Kashmir. Problems in tunnel. This is the Dulhasti project. Here also, it was the first TBM, the tunnel constructed through TBM, and it was run into problem, contractual as well as geological. Then Parvati 2 experienced very heavy ingress of water laden with silt, and initially it was a geological problem. Later on it was converted into a contractual problem. And now the project has been restarted and the TBM is working again. I'll take up each one of this maybe a little more detail when we proceed further. Then this is an example of a squeezing ground, rock bursting, and high temperature conditions in Dhaliganga project. But try to I mean, those of you who are not basically do the geological work, maybe in administration or maybe designers or engineers. In Himalayas, your geologist works in these kinds of conditions. You see, mostly about 90% of the areas are covered with very thick foliage. And the remaining 10% is also not visible to a geologist because of either it is also covered by riverine sediments or some kind of overburden, or there is accessibility problem. So these, small rivulets or nalas as we call in Hindi or Nepali, these are the traverses which are the only thing which are available to me, to us. This is a tunnel alignment. I mean, this is the actual topography of a project in Bhutan. So, out of the 10%, you construct a geological model by observing hardly 1 or 2% of the rock. And then lot of tender specifications and design requirements are to be fulfilled. Rest 99% is almost an imagination, or it comes through the geological interpretations, whatever knowledge, geological knowledge or structural geology knowledge you have. So this also must be kept in mind, because many times we say that why it was not known earlier. I mean, this is the reason you can't know it. Management is required. And the only key, I mean, whatever contribution I can make, because there are so many people who can either make a very happy situation or make the problem even worse. So the only key is to collect best possible geological and geotechnical data and select a layout in consultation with civil engineers which has minimum hazards, and to adopt measures to reduce impact of surprises if they come. So therefore, comprehensive exploration or investigation is required. In India, we normally, the standard is allocating about 2% of the project cost to the investigation. But practically, it seldom happens. During the actual investigation stage, I mean, most of the projects have spent around, say, around 1% or so. So, I mean, those who are planning the investigation, they must try to explore to the maximum and try to utilize the maximum allowable funds. Because many times, we become intelligent, we are saving so much money, but if you are saving some peanuts, you will have to pay in gold. Then sufficient time is to be given for preparation of the original document, which is known as the detailed project report, which embodies the geological exploration, the construction material investigation, hydrology, everything. Many times I have found that during this phase, entire department is after the blood of the geologist, why this is being delayed, why survey is taking so much time. And after DPR is completed, then for 2-3 years, it will remain in a shelf and nobody will bother about it, or it will be going through several phases of various types of mandatory clearances. So when you can give so much time there, give some sufficient time to project investigation also. And if that is done, I'm sure projects will not face problem during the construction, and the risk which increases because of lack of investigation will also be reduced. And if you see this diagram becoming lighter and lighter, and maybe that they will not remain as big as we experience in time. So you see, I come down to my first case study, which is Dholi project, and I have chosen this project for two reasons. Because this was the project which really involved me for about more than 5 years, and this is one project where I worked right from investigation to construction, finalization and commissioning of the project. And the second reason is that this is constructed on a tributary of River Kali, which is the boundary of Nepal. I think all students of geology in Nepal would know. So in this slide, this side is Nepal and this side is India. And I camped here for more than about 7 years or so. So this is Kali and this is Dholi Ganga. This is the dam of Dholi Ganga here. It is a 56-meter high concrete face proper. The first concrete face proper dam constructed in India. Then desilting chamber. This is our headless tunnel, about 6 kilometers long. And then this is an underground powerhouse. And then this tail race discharges water in a small tributary, once again, of River Kali. Because of international restrictions, we discharge our tailwater in our own territory. So this was the project which involved several lessons for us. You see, the dam, which I said the 56-meter high concrete face proper dam, was to be constructed here. This is the axis of that dam. This hill, this is the right abutment of this hill. Here a very low level chute spillway was to be constructed, and this is about 150 meters high hill. The height of the spillway cut slope was 120 meters. When we started our first excavation in the top portion of the hill, we experienced multiple rock failures. And this is the actual photo which was taken on the next very day when this entire area experienced this massive landslide. And this forced us to change the design. This is our original design. This is where we started our excavation. And this was a steep slope. The design slope was, the ruling slope was 1:3, and it was then made gentle at 1:2.5. You will see that every bench has been made gentle. Then we provided about 15 meters long anchors. So with this, although there are so many things to share in Dholi Ganga, but to save time, I will proceed to another one, which is in Jammu Kashmir. You see, this gave us a different type of nature. The project was difficult, but could be constructed with some ease and without much complication. And without any hesitation, I would share that, you see, when we were negotiating the contract of the tunnel with our contractors, which was Hindustan Construction Company HCC, we told them that geology is very uncertain. We don't vouch for the geological data which we have given. The reason being, this entire area is difficult for geologists to roam around because of security concerns. And the area remains snowbound for more than 10 months. So therefore, there was a lot of uncertainty involved. And because of that, you see, when here, this tunnel was around 23 kilometers long, and out of that, 14 kilometers was planned through TBM. So that was the main concern. And we had a bad experience in Dulhasti before Kishan Ganga, and we had a bad experience in Parvati. So therefore, we thought that we must address this issue in some another manner. And that was providing provisions in our contract to deal with squeezing ground, high stresses, high temperature, fault or shear zones, or heavy risk. You can see that the measures which have been kept in the contract. It pays. There was a lot of flexibility in the contract, and finally, the result was that we chose a double sheet TBM, and which had a lot of good features for, it was having adjustable excavation diameter. There were 2 sheets for dealing with the squeezing conditions. I'll not repeat all this because I think people who know TBM tunneling would be knowing that what are the advantages of double sheet TBM. It was a good choice, and as a result, we started this excavation in May 2011, and it could be completed in June 2014. Just in 37 months, it was 7 months ahead of schedule. And not that we experienced or we encountered very good rocks. I mean, this was also part of Himalaya. It was also having all those fragile and young and all kinds of rocks, whatever adjectives we use for Himalayan rock condition. It was having all good things or bad things, but the management was better. And as a result, you will see that in 1 month we got around, it was exactly 812 meters progress through a TBM. It was a record in a month. And the average progress was around 400 meters. And this is a breakthrough through the TBM in Parvati. This was once again a double sheet TBM. Now, you see, what can be done from here onwards? Maybe that in exploration or investigation, if we can use airborne geophysical survey and LiDAR, it will be good. In India, still, we are shy of using these directional drilling or long drilling. Although we are capable, there is a myth in this part of the world that we are lacking in our drilling capabilities. No. As head of Mineral Exploration Corporation, I'm having a fleet of 70 drills, and most of them can drill more than 1,000 meters. And there are 6 drills which can go as deep as 1,500 meters. And we are doing this exploration in several other mineral exploration projects. But somehow, I don't know why, in hydropower sector, these resources which are available have not been used. And I urge upon all of you who are associated with the upcoming project, wherever there is a need for deep drilling, you may approach Mineral Exploration Corporation. Although after tomorrow I will not be there. So you will have to approach somebody else. Well, how much investigation has to be done? You will see that as you go from 0% to 100% of acquisition of data, the risk reduces to an extent that it becomes 0. But this 100% acquisition of data cannot be achieved. And secondly, as this acquisition of data increases, the cost increases, and then it shoots up after the 60%. So this intersection may be a optimum level of exploration. This is after a ISRM paper where they say that if we do a good exploration, 60% of the geology can be known, but rest of the 40%, in my opinion, this 20% should be taken care with flexibility in the contract, and the balance 20%, because this 40% will remain unknown. Right. So, therefore, this approach of Palmieri, he came to India in 2012, and I listened to him for the first time. He applied this approach in context of hydropower, where he said that there could be some known knowns. In my opinion, these are those 60%, certain provisions in the contract, and then unknown unknowns. We really don't know. And these are, to be fair with this, I'll say that these are the surprises, but with good investigation, we can convert unknown unknowns to either known unknowns or even known knowns. I mean, this is how we can, yeah. So to conclude, good geological investigation, this is the backbone for a project. Comprehensive geological investigation is to be planned project-wise. It is a site-specific job. You can't make it a standard a checklist and proceed with this. Then, if the exact location is not known, at least know the area where some kind of risk is there, and adequate provisions in the contract, in the pre-construction stage exploration is a must. And then provisions for carrying out geological investigation during construction stage also must be kept. There should be some fund available during the construction stage to face the situations. Thank you very much. Thanks for a very patient listening. This is almost a last cricket match for me. Thank you very much.
I was interested in the Krishna Ganga Tibium tunneling part. You said that the copperhead design was best for hard rock and soft rock as well. So what was the copperhead design, the special design for hard and soft rock?
You see, a lot of tests were performed. I mean, after we laid down the specification, our contractor did a lot of chasseur tests. And based on that, the cutter heads were designed. I can't share with you the exact details of those designs because these are the private to the contract.
No, no. I would like to ask one very relevant question to your session. Like, just example, like while construction of the hydropower dam, let it be like a diversion dam or reservoir dam. Suddenly, if you face the geological surprise, like one side of the dam is moving, I mean, like it gains some gravitational pull and then it is in the motion. What will be your immediate reaction? I mean, like mitigations, or what you will think to put some measures to stop that? So, if sir could elaborate on this particular topic, it would be great, since I'm facing some similar kind of problems in our country.
I think if I have understood you correctly, you are asking, in case suddenly you come across a situation where one block of the dam is started moving or it is becoming unstable, what should be done? Is it the question?
I mean, like one side from like while construction of dam, we have to
one side or one abutment is moving. Are you?
Yes.
Okay.
Yes,
I mean the side slope is moving.
Yes, side slope is unstable. Certainly.
Yeah. When you start excavation, right? You see, these are the common problems, and we had faced it several times, particularly in those parts of Himalayas, and Himalayan rivers are normally flowing through very deep gorges. So, yeah, in the initial part of design, you have two choices. Either you increase your excavation to make stable slopes in the beginning of the construction, or you go ahead with a steeper slope and then you make some provisions and make a gentle slope. I'll go back to the slide which was shown to you. It was a similar problem. I had just, can somebody help me in bringing that cut slope slide of Dalivanga? Vivek, you can help me. Yeah. You see, this is what a contract should provide for. Because you thought that a particular cut slope with a particular elements of support system like rock bolts, shotcrete, or some width of benches and bumps will be sufficient. And you found that it is not suiting to your condition after you started excavation. Well, I think exactly a similar situation was faced here. This design was not suitable. So therefore we made it gentle. The problem is when the situation will come, some time loss will be there. But one should be ready for that. There's no point in continuing with the same sort of design, and then in case we would not have stopped here, maybe by the time we were here, this entire mountain would have moved. So as you progress, you need to improvise your design. You need to once again recalculate whether the forces taken in the support design, whether the soil properties, because when you initially do your testing program, you do not have the good representative samples either. So C and Phi plays a major role here, and then review your design. If you do that, all problems can be solved. Thank you.
I am Adar Singh Mahara from Nepal Electricity Authority. First of all, I will like to give a lot of thanks, Dr. Dhawan. And I have one curiosity about the high heat problem in the tunneling, like in the Dhauliganga. And I know that the Dhauliganga project is nearby the MCT. And there are so many hot springs, we say the Tatapani. And my curiosity is that what is the problem when the excavation is, whether just the height problem is during the excavation or after the excavation or during the operation? Just the labor problem in the excavation or in the operation, if there is the high heat regularly supplied by the MCT, then the water volume will be increased, or we cannot supply enough discharge, I mean the design discharge. Or when it is any repair in or shut down the powerhouse, the tunnel will be empty, if suppose, and at that time, whether it will be the support effect or such type of any problem,
You see, certainly a very practical problem for Himalayan geologists, because you referred to MCT, and there are certainly a lot of hot springs all around in the entire length of Himalayas. But in Dhauliganga, I must share with you, these were mild temperatures, not very high temperatures. And although in some other projects, like in Sanjay Gandhi, in Nagpur Chakri, there was, temperature conditions were still higher. And wherever these are such kind of conditions, you have to do a lot of, push a lot of air and maybe provide some kind of, ice so that the temperature is down. You asked whether it is experienced during excavation or it continues thereafter. Well, it is experienced only during excavation, and thereafter it is none of our business. The tunnel takes care of it. A lot of water comes and nobody knows that whether there is a 0.001 degree change in the temperature. So if you can construct your tunnel safely, because this is the ease of the people, the construction crews, because once the temperature increases more than 40-42, it becomes very difficult for them to work. They sweat a lot. I have seen, entire crew working just in their undergarments because they can't wear. There's so much of sweat. So it is a problem.
just a liver problem.
Thank you very much.
Okay.
And
How about a round of applause for Gopal? And so at this time, I would like to introduce our second keynote speaker, who has been a friend of mine for 11 years. And this is Dr. Fashuan Wu, or in China, Wu Fashuan. He has his bachelor and master's degree from the China University of Geosciences, and then his PhD from the Chinese Academy of Sciences. He wears two hats. He is a professor with the Chinese Academy of Sciences in engineering geology, and now more recently he's at Shaoxing University, where he also is a professor there. He has been the Secretary General and Vice President of IAEG. He's done a wonderful job. His team running the Secretary General's office has done a wonderful job for IAEG. He was a Vice President when I was Vice President. And in China, he has been chairperson of the IAEG China National Group. He also won the big award, which is the National Award for Science and Technology He has been an honored scientist from the China State Council. His focus is on rock mechanics and then also on rock engineering geology. And he is one of the developers worldwide of this new area of statistical rock mechanics, and that's what he is going to be talking about today. He has done many projects in China. One of the ones that I think everybody in the world knows about are the Three Gorges Dam. And in back of it, you have all of these slopes. He has helped design 2,760 slopes in back of that using his statistical rock mechanics approach. And then he has worked in railway projects, also hydro stations. He has been a great friend for many years. He has a lovely wife who is here, and his son presented a paper yesterday. So his son is following in his father's footsteps. How about a round of applause and a welcome to Pak Hong.
So, I'm very pleased to give this presentation here entitled Statistical Mechanical Model for Rock Mass and Applications. Okay, so I talk about it in three parts. Firstly, why SMRM? You can see that SMRM is, so as we know, half of infrastructure constructions is on or in rock mass. So a lot of things we need to do with rock mass. But as we know, rock mechanics is the fundamental, is the theoretical support of all the rock mass project designing. So the aims of rock mechanics is to describe, analyze the geological structure and the behavior of rock mass with various of types of rock mass and the existing stages, the environment of existence includes geostress, groundwater, weathering, unloading deformation, and engineering environment. Sorry. So, sorry. So, we can find that every kind of different kind of rock mass with different structures. What's the geological features and how they behavior, how they deform, and what's the strengths and the mechanical activities. This is what we want to know. Yeah. So, but what the rock mechanics doing now? So, you can find in the books to describe separately for rocks, joints, stress, and groundwater, and etc. Separately. And we will need to do the analysis and design by theory and by brain. No? So experience is much important. So without a geological way of thinking, so this is the problem with the rock mechanics theories right now. So and another aspect that the way for the engineering project designing what we are doing. Firstly, we get I cannot point it. So, firstly, we get some base parameters from the field, the UCS and the joint system, and we get a base classification of. Yeah. Okay. We get a basic classification of rock, and this is a reduction from the block, integral block, and then we consider stress and water reducting again, and we consider engineering factors reducting again. So all the processes are reduction from the intact rock to the rock mass we design. So this is what we do in this engineering geological design. So we have no perfect theory to explain the behavior of rock mass on the basis of geology, geological features. And for the quantification, we need to calculate, we need to quantify the theory. This is the most urgent task for engineering geologists, to quantify the theory of engineering geology. So we need quantified rock engineering geology. This would have been here SMRM, based on the geology. So the first part, the second part is a series of models of SMRM. SMRM, as I mentioned, the statistical mechanics for rock mass. What is SMRM? It is the rock mechanics based on geostructure of rock mass and considering the geofactors. So you can find that this is the framework. So this is the core part of this. All the theories are based on structure theory, structure models. And then based on this, we can get the stress strain models for the deformation behavior, and then for the strain theory for the strains for the failure of the failure criterion, and for the hydraulic models for the permeabilities and the dynamic models. So all these things are these two set up based on the structure theory. And we will consider at the same time the geo-environment and put it in the applications. So firstly, the structure model of rock mass. So firstly, we get basic information, basic data from the field, includes this continuous network measured by scanning line and processed by the geometric probability. At the same time, we get some information for the intact rock with some mechanical tests in the field for the parameters. So based on the data from the field, we can establish a series of models to calculate the geometric features of the rock mass. Firstly, we need this index. You're very familiar with the GV, and this is the density, volume density of the rock mass. That is determined. Also, we can get RQD in different orientations in the floor space by this diagram. So we know different direction with different values. So we can get the maxima, minima, and the average, and also the anisotropic index for the RQD by this. If you point any point here, you can get a section. You can know the change in the section of RQD value. So we can also get the hydraulic connectivity, the index for this from our metric models like this. And we can also get the maximum size and the opening of joints of a joint set. This is the distribution of the maximum size of openings. And at that point, at the peak of the curves, we get the maximum volume of the joint, size and opening. All these are very important index for, sorry, what's the problem? Okay. Secondly, we can get the stress-strain relationship for deformation and analysis. This is the 2D or plane models. I just make a very simple explanation. If we have a unit here act as stress, so the block will deform, and the joint will also compressed and shear deform. That, we get the displacement for the compressive displacement, and then the shear displacement. So we get the strain energy in this block, and also the intact rock. Combine all these two parts, This is for intact rock, this is for the joint system. We get this relationship from between strain and stress. So for the 3D model, it will be much complex. I will not describe more. But by this way, we can easily get the Young's modules for rock mass, like in this way. This is the formulas for the Young's module of rock mass. So by this way, we can get the force spacing Young's module in different orientation, and also same time the maximum, minimum, average, and isotropic, and weakening. Weakening, what do we mean weakening? This is the Young's model for rock, intact rock. This is for rock mass. This region just reflects the weakening of the rock mass. And this is the effect by the confining press. With different confining pressure, we get different Young's module for rock mass. So this the same. So you can find in these pictures that this is with some very lower, 0 confining pressure, and then 1 megapascal, 2, 3. You can get that this is the maxima and this is the minima. With the increase of the confining pressure, get the same, totally isotropic. Okay, this is in some realized factors affecting the elastic module of rock mass for different angle, different direction, and different radius, different density of joints, and the friction angle of the joint surface, and the normal stress, different normal stress. For point radius, also very important mechanical parameters. So we can get from the constitutive model to get a formula to calculate point radius for rock mass. 2 things we need to pay attention to. This the angle, they reflect the change with the orientation, and this is the value. You can find that is changed in different direction. And then for the compressive stress, the point ratio can reach can be more than 0.5. It's not cannot understand, and even 1.0, big than that. And for the tensional stress, it will be less than intact rock. And they show that in X direction and Z direction with different volume. This means there is also an inisotropy in space. And for permeability, we have also these formulas to calculate to get the stereogram in different things. The same result, and the same for some special sections. And this is some result for stress fluid coupling with the increase of the stress, the permeability will reduce rapidly. And then this is some size effect, as you know, with the size of the object, the permeability will increase. Fourthly, the strength of rock mass. So we consider in this way. This for the block, very familiar. This formula, and this for a set of joints. We get this criterion for the strength, and combine this, we get the formula for the rock mass. Also, the stereogram, I have not mentioned too much. And this to show that this is the strength of rock block. And this is the average between rock block, intact rock, and the joints. And this is for the weakest link. As you know, the joint is the weakest one. Weakest units decides the strength of the rock mass. And this is to show the size effect of strength. You can find that this the volume and this the stress. With the increase of volume, the stress is decrease. Very familiar regulations. And another, you can find it in the formula. The V means the volume. So for the and another effect is the confining pressure effect for the strength of rock mass. The red one is some stronger direction, some higher strength, and the blue one is some lower. So with the increase of the confining stress, this be wider, so the average strength of rock mass will be increased. The fifth one is the classification of rock mass. This is a very currently used method in rock engineering. So we have got a serious method for rock mass classification. RQ, BQ in China, and a series of others. We have already got that. We have also get a relationship between the classification and the mechanical parameters. So we have developed the web software for different systems for rock mass classification. It's not over here. BQ from China, RQ, and Z from China, SMR team. We can classify the rock mass by any of them. And this is to show the classification system by SMRM. So if you want the classification by SMRM, firstly you need to calculate the elastic modulus of the rock mass, and then you point a special point and then get the volume here and press. It will automatically create the rock mass classifications. And we have done a series of comparison for the different system rock mass classifications. So here is a series systems, and then this is for the SMR systems. So we do the comparison from, if you get the elastic modulus, you can get different the volume for other systems. So we compare that very close. And if you get the classification of the rock mass, you can get the elastic modular and fractional angle and the cohesions. So another use is application is the zoning for slope unloading deformation by the alien. So as you know, the slope we will have some unloading deformation. Near the surface is much stronger. When you get into the slope is reduced. So we have developed the formula to calculate by the accumulated opening to get these curves. For these deep parts is the strongly unloaded parts, and then reduce. So some numerically simulation result. Firstly, for the column with one set of joints. The deformation will take like this and symmetrically. And secondly, we compare with the same set of two sets of joints. It will get down, first get down, and get fat, the top. So this is for the slope, the building slope. I have the videos here. I cannot. And we do some simulations for tunnels with one joint set in this direction. So generally, in the gravity action, so the tunnels will compress in this way. But if we have this one set of joints, it will compress in this way, not in this way. You can understand that? Okay. So there's some models for SMRM. The third part I want to talk about some case studies. The first story is around the rock mechanics classification adjustment for tunnels. As you know, so many railways are under construction now, so with many thousands of tunnels. So in the mountain area, the tunnel will be very deep buried, so with very strong geological stress, so there we may have serious problems. So the first one is the tunnels in the northwestern China, northeastern China, and this is the northwestern China. Serious, more than 40 deep tunnels have some big difficulties. So this you can find some the rock is some special, very soft layers like the rock mass. So firstly, in the investigation stage, they have got some data for the rock mass classification. As you know, this is a normal way. Firstly, classification and then design, some standard design. So firstly, they get some data and rock mass classification for the design. But according to this, the data, the design, when they excavate the tunnels, the problem occurred. Almost most of the tunnels, the lineages of the tunnels failed. You can find that this is the first living, and so what's the problem? Yeah. So you can start serious failure phenomena, and even the second for permanent linear system are breaked like this in this way. So it's very terrible. Therefore, you can find that this is at least in some railway line. We just list about 10 tunnels. So this is a read. This is a read for the upgrade. Why they need to upgrade the classification? Because the design just according to the classification of rock mass. So here in the first stage, the classification is too high, and this is why the tunnel dealing system breaks. So they need to upgrade the classification of rock mass. So this means a lot of money. They need to apply the increase of investment, a very big number. You can find this system, this percentage to modify, to upgrade. So this is not money. So when we submit the application to the government, the governor asks them, what are you doing in the beginning? Or what's the problem with you? So why so many tunnels to the rock mass classification should be updated? So they asked me, my group, to do something, to help them to explain the reason. So very simple. At the beginning, at the investigation, we get very little data, just from some borehole. We cannot get enough money. This is first reason. And the second reason is excavation. Excavation will make the stress fields changed, redistributed. So they disturb the rock mass, make the strength and the mechanical property be better. Bad. So this is this example for one of the tunnels. Here, we did some calculation for them. All this data is for the fields, and then some calculated data, and finally we get the class of some rock mass. But the original is number three class, and we get 5 class, 2 classes difference. This means a big money. So this is the first story, and the second story is that the rock mass parameters calculation. for some hydropower station in the eastern China, within China. No? So this is the site. This is the site of the project with very many areas. So we can get some data from there. So firstly, we did some zoning for the slope anode deformation. By this we are just use and a grouping of the joints. We have time? Okay. And then the distribution of joint size, spacings, spacings, and openings. And force space RQD and force space UCS of rock mass. And the force space elastic module of rock mass, and the force space with different confining pressures. Oh, this is the second story. So as a conclusion, I need to say we need the rock mass mechanics to explain the geologic feature and the mechanical behavior of rock mass. Statics mechanics for rock mass has established a system for that. It can fully reflect the anisotropic geomechanical behavior of rock mass. And SMRM provides some comparable method for different rock mass classification system. Thank you.
Agency called CSI in Australia. It's an excellent talk. It looks like you have developed formally for everything from acceptance models to Poisson ratio. Just I'm wondering, as a field engineer, what sort of effort we need to spend in the field as input to your program? That's one question. And I think after the talk was statistical mechanical sort of mechanics classification. So it was very hard for me to read the figures from here. In your program, does it just give one value for example, Young's modulus, or you will have a statistical distribution for the Young's modulus?
So we just want to provide the system for you. It's a software and some hardware to get information from the fields, and then we have a calculation system as a software in the server computer. So that will make you very convenient for the field work. Okay. The second question.
The second question I'm asking is rock mass is so heterogeneous, right? We can't just be relying on one value for Young's modulus or experiment or something. And the title of your presentation also talks about the statistical sort of sense. So just I think like maybe I didn't read your figures properly. So your program, does it just output one value for each of the parameters, or you give a statistical distribution of the parameters? So for example, like me, I can use that distribution and use Monte Carlo simulation or something and come up with saying, okay, that's the factor of safety range for me. Or I can talk after during the cheaper.
So in rock mass, you can get one number, but he needs a statistical distribution of the values, and that's what your program does. So it does do the statistical distribution, which is much more meaningful, yes, than one number, which is, because as you mentioned, it's very heterogeneous, and so one number doesn't do it.
Okay, thank you, thank you.
Thank you.
Just now you mentioned that the Poisson ratio you can predict more than 0.5 even to 1.2. Is it right? The right statement? Because the Poisson ratio maximum should be 0.5 is a water. What's the state of Poisson ratio beyond 0.5?
It's a story. As you know, the past president of ISR wants to be the science. So I submit a paper, just describe the poison ratio, which can be bigger than 0.5. He almost refused this and kept it and review for 2 years. And then suddenly he informed me that I can't publish your paper because he received the paper just described the failed testing, not verify this phenomena. Why the poison ratio can be bigger than 0.5, just like in the continual system means the water. So you know the block of rock mass with serious joints. When you press it, the joints will be slight. This make the deformation will be very, very big, very easy. So this is why you can make the poison ratio bigger than 0.5. Yeah.
Well, how about a round of applause for Fashwan Wu?
Now we are in the
Yes.
end of this session. First, before ending the session, I would like to honor our keynote speaker by some token of appreciation. For this, I think I am looking here to two of our NGS colleagues are here. Our president is here and co-convener is here. That's why I request Dr. Kaviraj Paudel to hand over the keynote letter of appreciation to keynote speaker, Dr. Gopal Dhawan. I request Professor Farquan Lu. Taking from the hall. And we have a program, as we know, we have a very colorful program book and it has a very colorful mistakes also. So what I have to say that we prepared the new program. You can have from the registration desk or you can have just outside of this gate, there is a marble table that from there you can take the revised program from there. And our exhibitors are complaining us that nobody are coming here. Only 10 people, 20 people are coming there. They are just complaining me that no, it's no use to put the booth here. So please visit their booths and suggest them or just try to learn what they are doing in their company. And meantime, we are having one very special booth from International Geological Congress 2020 IGC. Okay, please visit the booth. Two gentlemen are there, and we have one presentation also in this in the second keynote presentation session. Please don't miss the introduction to 30th IGC Geological Congress information. Okay, good morning again. Now this is for keynote presentation session 3, and in this session we have 3 presentators, and now presenters are already here and they already uploaded their presentation. So I would like to request Professor Dr. Suichi Hasegawa to chair this session. Professor Hasegawa is Dean of Faculty of Engineering in Kagawa University, and we together works a lot for the Himalaya, and we published few papers for the Himalayan landslide issue. And he used to say that I was born in Himalaya 1,000 years ago, and again he had a rebirth in Japan, and he believed that he used to be a yogi in the Himalaya. So he loves Himalaya a lot. So that's why I think today he will enjoy a lot about the presentation that we have today here. Thank you, Professor Suichi Hasegawa. And we have co-chair, Dr. Ananta Prasad Gajurel. Dr. Gajurel did his master's from Tiruvallur University, and he did again his master's from Joseph Fourier University, France. And he did his postdoc from Cornell University, United States of America. He's teaching right now. He's as an associate professor. He's teaching in Tiruvallur University, and he has a teaching experience of more than 25 years. He also taught me in my graduate course. He's my teacher. And he's specializing in the research in sedimentology, geochemistry, paleoseismology, Himalayan geology with French, American, Swiss, Japanese, Indian, and Chinese scientists. So much experience. Okay. Now, thank you very much. Please, and if we have a reporter here for support, Miss Tara Pokhel and Mr. Manoj Khatiwala. Okay? Yeah, Manoj is here. Okay, now, floor is yours, Professor Hasegawa.
Thank you, Raja, for kind introduction. I'm Suichi Hasegawa from Kagawa University, and we chair this second keynote session. We have 3 keynote presenters. Each speaker has 25 minutes for presentation and 5 minutes for discussion. It's a great honor for me to introduce Dr. Fausto Guzzetti, outstanding landslide researcher today. He is the director of National Research Council, Italy. Dr. Guzzetti graduated in geology from the University of Perugia, Italy, in 1983. In 2006, he obtained a PhD in geography from University Bonn, Germany, with a dissertation on landslide hazards and risk assessment. He was the president of Natural Hazard Division of the European Geoscience Union and has led European and national projects. A founding member of European Geoscience Union, Dr. Guzzetti has president of the National Hazard Division of IAEG between 2002 and 2007, and he is the executive editor of the EGU journal Natural Hazard and Earth System Sciences. In 2008, he received the AGU Union Service Awards. Dr. Guzzetti is the author of or co-author of more than 75 papers in international journals. 10 book chapters, 9 landslide map, and several communications to national and international conferences.
So, Dr. Guzetti,
My talk, as you can read, will be on the challenges of operational forecasting on early warning of rainfall-induced landslides, and it will be in 5 parts. First, on the prediction of natural hazards, including landslides. Second, on rainfall thresholds, which is a way of predicting landslides. Third, on the experience we gained in operating. So let me discuss the prediction or forecasting of hazards, and in the talk I will use the 2 terms as synonyms just for simplicity. The problem of predicting physical phenomena, including landslides, using a scientific approach, is actually an old problem that in modern terms dates back to the 19th century. Heinrich Hertz, a German physicist who proved the existence of the electromagnetic waves, one wrote, and I quote, "The most direct problem which our conscious knowledge of nature should enable us to solve is the anticipation of future events, so that we may arrange our present affairs in accordance with such anticipation." And interestingly, Hertz even told us how to do this when it wrote, "As the basis for the solution of this problem, we always make use of our knowledge of events which have already occurred, obtained by chance observation or pre-arranged experiment." Before I go further, we should recognize that natural phenomena are not equal when it comes to our ability to predict them. We can identify 2 broad classes of phenomena: those characterized by high predictability and low randomness, and those for which predictability is low and randomness is high. To the first group pertain the motion, for example, of a bullet, a planet, or the pendulum you see in the slides. For this phenomena, the observation of many events is useful to make predictions. Indeed, it was through repeated observations that the physical laws that explain the behavior of these phenomena were formulated. I will make 2 examples. 3 objects launch at the same velocity with different angles follow trajectory that we can predict very accurately. The second illustrates the second law of Kepler that predicts the position and velocity of planets and satellites, natural and man-made. You may think that these are trivial examples. Well, think again. Wars were won and people went to the moon and came back using the equations behind these simple examples. There are other phenomena, including meteorological, climatic, geological, or biological phenomena that are characterized by an intrinsic high randomness. For these phenomena, the observation of past events and the analysis of time series may actually not be useful, and it may even be misleading for our prediction. Let me give you an example from hydrology. This graph shows the annual peak discharge of the Danube River in Vienna, Austria, from 1828 to 1900. You may argue that the frequency of high discharge floods, those that are marked by red circles, was increasing at the end of that century. But what do you say if I show you the full records from 1828 to 2008? Much more difficult to say. And then, what does it mean to predict a hazard? A problem is that it may mean many different things, including, for example, to anticipate when or where an event may or will occur, or how intense or destructive the event may or will be. These predictions are all different, but are they useful? Well, let's see. If I say, tomorrow there will be a landslide, I am certain to be correct, to be right. I have not said where, and every day there are many landslides globally. Even if I say tomorrow there will be a landslide in Italy or Nepal, and I'm smart enough to say it knowing that tomorrow it will be raining hard, I stand good chances of being right. There are hundreds of rainfall-induced landslides every year in Italy, and I presume also here in Nepal. So these predictions are actually both correct, or can be both correct, but they are not very useful. Instead, should I say, in response to the expected rainfall, in the next 12 hours there will be 50 landslides with a volume larger than, say, 10,000 cubic meters each at a given site. I will tell you where, when, how large, and how many landslides to expect. This will be a useful prediction that, unfortunately, today we struggle to do. This doesn't mean that this prediction is impossible. It simply means that we cannot do it. We don't know how to do it today. Let us talk more specifically about the prediction of rainfall-induced landslide that is possible using, for example, rainfall thresholds, which will be the subject of the second part of my talk. Traditionally, thresholds have been defined as visual lower bound of empirical rainfall condition known to have caused landslides. And the graph here shows the first, as far as I know, rainfall intensity, rainfall duration threshold that was proposed by Nell Kane in 1980, and the first event cumulated rainfall duration threshold proposed by Jan Innes just 3 years later. These were groundbreaking works by amazing scientists at the time, but they are problematic to use in an operational environment, and similar thresholds also. A first problem is the definition of a rainfall event. What is a rainfall event? When it ends, and even more difficult to say, when does it start? We have proposed an algorithm for the objective definition of rainfall conditions that have resulted in known landslide, and a part of this algorithm consists in the objective definition of the rainfall events from a simple rainfall record. This graph here shows nearly 340,000 rainfall events in Italy from 2002 to 2012, obtained applying these algorithms to rainfall records obtained by a network of 1,962 rain gauges in my country. You can see that the events, which are the single green dots in the plot, cover a large range of rainfall duration and event cumulated rainfall. When we combine the event rainfall information with information on the time of occurrence of landslides, we obtain the second graph that shows 2,309 rainfall events with landslide, one or more landslides in Italy. In the plot, each dot represents a rainfall event with landslides, and the two maps shows the location of the rain gauges and the over 2,300 landslides used to construct this plot. And here we have a second problem. There are many possible curves that one can define as lower threshold, and most of them are reasonable, at least in principle. So how do we select the best, or at least the optimal threshold for possible landslide occurrence? All this means is that, for example, we expect 5% of the gray dots to be below the blue threshold and 20% of them to be below the yellow or the orange threshold. A third problem we have is that thresholds are affected by uncertainties, which is important to quantify. Something that, unfortunately, is not it's very rarely done in the literature. Here I show 3 cumulated event duration thresholds with the colored areas showing their inherent uncertainties. And considering this uncertainty, the threshold overlap, so they cannot be separated from a statistical point of view. And this is important to know when using these thresholds in an operational environment. Being geologists, we know that the thresholds are or should be affected by environmental conditions. And we have defined the thresholds for different thematic subdivisions in Italy, including physiography, lithology, soil types, land cover types, but also climate regions and meteorological conditions. And this is the result. The plot shows 26 thematic thresholds we obtained. When shown in linear coordinates and in the range of rainfall duration, which is the one that is to us useful for operational forecasting, so basically in the range from 1 hour, say, to 48 hours, one sees that the thresholds differ, all the thresholds differ quite significantly. And this complicates their operational use. Let me move then to the third part of the talk that started when in 2008 the Italian National Department for Civil Protection, which is an office of the Prime Minister in my country, posed us this apparently very simple question. Can you forecast rainfall-induced landslides in an operational mode? To respond to this question or to this challenge, we designed and we keep running an operational landslide forecasting system. This is a threshold-based system that uses landslide and rainfall data, tools to define thresholds and their uncertainties, and criteria and tools for the validation of the forecast and to deliver the forecast to different end users, different stakeholders. The system is based on a complex, yet we think robust infrastructure that relies on standard hardware and open source software. This was a self-imposed user requirement to make the system portable and less costly, less expensive to maintain. The system compares hourly rainfall measurements taken by 2,650 rain gauges and rainfall forecasts available every 12 hours with predefined rainfall thresholds, and considering also landslide susceptibility. Every hour it produces a new forecast valid for the possible occurrence of landslide in the next 24 hours. These are examples of the forecast, in this case made on 28 February 2016 at 8 o'clock in the morning. Prepared use to your left the measured rainfall in the previous 96 hours, rainfall forecasted for the next 24 hours, and then a rainfall measurement and forecast modulated by a landslide susceptibility zonation of Italy, which we have. Shows hourly national landslide forecast from 8 September to 16 October 2015. It's a period of 38 days, about 5 weeks, for a total of 912 hourly forecasts performed in a fully operational framework or environment. I think there is a wealth of information here to be used, to be exploited for national scale landslide early warning. This other video shows hourly regional landslide forecast from 2 to 6 September 2014 for an area in southern Italy. For those of you who are a bit familiar with Italy's the Gargano promontory in Puglia along the Adriatic coast. This 4-day period included a 96 hourly forecast also performed in an operational environment. In addition here, the black dots show where and when landslide have occurred on the ground in this period, and you see that they did occur where and when the probability of occurrence that we predicted was actually quite large. Sorry, I messed it up. The system also works at the local scale. Although this is still highly experimental for us. For single rain gauges, the system traces the rainfall history in near real time. Every hour it calculates the probability of landslide occurrence for all rainfall conditions in the previous 96 hours, and then it traces the rainfall duration responsible for the largest probability. And I won't go into the detail, by using this complex set of information, we think we can use local warnings in near real time. Okay, are we satisfied by all this work? Well, yes, but only to some extent, because there are many issues that have remained open, and I will now mention just a few of them here. At the core of the system is an analysis of past rainfall events that have resulted in landslide and slope failures. Therefore, our analysis is only as good as the rainfall and landslide information, which depend on the sources and on how we collected and used this information. Surprisingly, we know very little about the quality of this information, both the landslide and the rainfall information. It may be different in other countries, but that's the reality in our country. When using past records for predictive purposes, we assume that the past is a key to the future. This descends from uniformitarianism introduced by James Sutton. I believe it was Scottish, at the end of the 18th century, according to which geological phenomena that occur today have acted in the past with the same intensity. And is this really true? It is actually something that is very convenient to assume, but very difficult to prove. And the idea has been challenged recently. For example, in a recent paper, Furlani and Ninfoem stated that, and I quote, present-day measures and observation may add uncertainty in the prediction of future trends. Our system is based on thresholds, or exploits thresholds, and this poses many questions. How many thresholds do we need? And how frequently should we update them? How do we verify the thresholds? Also, a threshold somehow assume an on-off, yes or no, zero black or white behavior. And is this adequate for operational forecasting, and particularly for operational forecasting of landslides? I'm not sure, I'm not convinced we have convincing answers to these questions. The system uses, and I told you this already, information of landslide susceptibility, and this map shows the landslide susceptibility for Italy we have prepared, one of the models we have. However, a review of the literature on landslide susceptibility modeling, which we have just completed, has revealed that typically models are not susceptibility models, are not constructed for early warning purposes, and may not be suitable for operational landslide forecasting. Just to make an example, it is totally unclear what is the type of, let's say, mapping unit that is best suited for operational landslide forecasting. An overlooked problem is how to go from forecast to warnings. In other words, how do we use the forecast in practice? A related question is, how do we select the warning levels, and how many do we need or do we want? This is relevant mainly because the performance of the system depends on the warning levels, their number and position, which typically depend on organizational, societal, and even legal constraints more than technical issues. This chart here shows a procedure, a flow chart, for the definition of warning levels in a threshold-based regional landslide early warning system in Campania, in southern Italy, the area around Naples. I don't expect you to read the chart, but I show it only to stress the complexity of this apparently very simple step. Then a vital component of any forecasted system is forecast evaluation. For a landslide forecasted system, this is damn difficult to do, and for a very, very simple reason. Lack of landslide information does not mean that landslides have not occurred in an area. It's not like for flooding or for earthquakes, for which we have spatially distributed instrumental systems. We can only be certain about 2 of the 4 cells of the classical contingency table. And this limits our ability to measure the performance of the system. What this means is that the standard metrics commonly used for forecast evaluation, for example, in weather forecast, are problematic to use when it comes to landslide forecasting. And do we have better measures? Well, maybe. Here, in this plot, I show 52 rainfall-induced landslide events that have caused fatalities. These are 52 fatal events in Italy between January 1996 and February 2014. These are the red dots in the plot that were all predicted, I should better say incasted, by the system. Is this a good result? We think so. We think this is a very good proof that the system works. But we recognize that this may be a matter of discussion. This brings me to which measure should we use? Quantitative metrics, qualitative criteria, like the one I've shown you. You can argue that that's semi-qualitative. Both of them. How do we define then an acceptable or an optimal performance level for a system? And then, most importantly, who should decide this? And this brings me to the last issue, which is that of transparency. Should the system be transparent to the user, to the stakeholders, or even to the public? Transparency helps building trust, and it may not be an option, actually. Yeah? But do we know what it takes to make a landslide forecasting system transparent? And what do we mean with that exactly? Very rapidly to the conclusion. I think the main lessons we have learned is that operational landslide forecasting of rainfall-induced landslide is indeed possible. But operational forecasting of landslides remains a difficult, uncertain, and complex task. Too many questions remain with too few answers, which overall it means a lot of work in front of us. And let me remind you that there are two groups of people who make predictions. These are fortune tellers and scientists. The difference is actually subtle, and is that a scientist can explain in a clear, unambiguous and transparent language how she or he makes a prediction. It is vital, I stress that, it is vital that we operate as scientists and not fortune tellers. And I like to conclude with these words by Peter Drucker, who is an economist who wrote, and again I quote, "Trying to predict the future is like trying to drive down a country road at night with no lights looking out the back window." And attempting to predict landslide operationally sometimes just feel exactly the same. Thank you for your attention and patience.
Very interesting presentation. Comment or question? Please give us your name.
Bangladesh actually trying to establish this source of warning system. There is none. So this is the time to start. And we're thinking the way you mentioned to help us is to get to think about establishing the. So thank you for your presentation. I have two queries regarding the response. The way you presented the two system, and you said operational system can work well, and how much response you are getting from the people, those who are living near to the landslide site? This is the first question. And secondly, do you have any recommendations for us? And how much cost it involved to start the process?
Thank you. To answer, and for two reasons. One, because it's really social dependent, so it depends on culture, it depends on the size of the population involved. So the reaction we may have in Italy may be totally different than the reaction you have in Bangladesh. Inside Italy, the reaction that we get in the north part of Italy, in the central part, in the southern part is actually different. So my suggestion there is to tailor the message based on the population. And there probably geologists, engineering geologists, engineers are not the best persons to do it. You need psychologists, sociologists, people that know how to communicate a message. This is very important to me. This system costed to develop not very much compared to other things, and one of the reasons we try to design a system that is transparent. One can look into the code, can change it, and we insisted in building a system that was inexpensive to maintain. All the hardware is standard hardware, all the software runs on open source software. You don't have to pay licenses, nothing like that. Exactly because we wanted as many people as possible to use it. I may deviate a bit now, but you gave me an opportunity to say, other communities, for example, the earthquake communities, have long gone through this way. And they have software, standard software that everyone in the world uses. And they agreed upon that. And I think that one of the problems that the landslide community has is this. Everyone develops his own piece of software instead of all together concentrating on something that we can then try in many, many, many different instances, have statistics that tells what works and what does not work, and then use it collectively.
Namaste, I'm Ojjwal Raghuvanshi from President to the board. I have one question to you, sir. Your presentation is really important because in context of Nepal, your analysis is based on the rainfall intensity and geology. In context of Nepal, there occurs lots of landslides even in the dry seasons. Can this tool be used for the landslides that occurs in the dry season also, which is not related to the rainfall intensity, something else?
Well, first, we are not using rainfall intensity, we are using rainfall duration and cumulated rainfall.
Yeah.
And the reason for doing that is twofold. One is that intensity depends on duration. So when you have two variables on a graph, the same unit of measures on both graphs is not very clear. Millimeter, not 10 millimeter in 5 hours, which is difficult. The system is meant to forecast rainfall-induced landslides. It will not predict, for example, snow melt-induced landslides, earthquake-triggered landslides, all that thing. We build into the system things like that work in Italy, like the thresholds are tweaked and are lower typically if it rains on an area that was interested by forest fires, because international literature suggests it's proved that there the thresholds will be lower. But if you have landslides that are caused by triggers that are different from intense or prolonged rainfalls, the system will not be helpful, of course.
In his service career in the Geological Survey of India, spanning for 37 years, he carried out geotechnical investigations of several river valleys and communications project and studied over the 5 damaging earthquakes. Dr. Pandey was represented GSI in several national and international committees, including global earthquake models. He was a member of peer group of consulted for first revision of vulnerability atlas of India. As a consultant, he has carried out seismotectonic evaluation of a number of river valley projects in the eastern Himalaya and Middle East. Dr. Panda has written over 50 technical papers and authors edited several major publications of the GSI, including the Seismotechnic Atlas of India. He is a member of the Indian Society of Engineering Geology and IAEG. His keynote title is Seismotectonics and Seismic Hazard Potential of Northwest Himalaya. Dr. Pandey, please.
As you can see, the title of my presentation is seismotectonics and seismic hazard. And after emerging from the technical part of the lecture, I will concentrate more on the societal issues. I think this is clear to most of us. Come to my technical part of the presentation. I think this has been shown by Dr. Gopal Daman, but to make things clearer, I'll concentrate once again on this. The Himalaya has a length of about 2,400 kilometers and a width ranging from, say, 200 kilometers to 400 kilometers. It is on the west marked by the Nanga Parvat range, which again is skirted by the mighty Indus River. And on the eastern side, we have got the eastern syntaxial belt, which is marked by the high Nangsha Barwa range. And here, the Brahmaputra flows from the territory of China into India. Now, I'll be taking up this particular portion in my presentation, and that we call as the northwestern part. It starts from, you can say, the Indus River and terminates at the Indo-Nepal boundary, which is marked by Kali River here. And this entire 2,400 kilometer segment of the Himalaya, which is, you can say, the youngest of the mountain ranges, includes in its territory the countries of Pakistan, India, Nepal, Bhutan, and China. So Himalaya has got a lot of significance as far as various geohazards are concerned, and so you can say we must have an integrated system of study, because if you work in isolation, we will not be reaching at the right solutions. Now this is, you can say, a seismotectonic model. This is the moho, which is occurring at the depth of, say, about 33 kilometers below the Indian subcontinent. And when you come to the Himalaya, it becomes much deeper, say 65 to 70 kilometers. Below the Tibetan Plateau region, it is of the order of 65 kilometers. And when you go further north into the China territory, in the Tarim Basin, it is again of the order of about 60 kilometers or so. Now this is the geological map of Northwest Himalaya prepared by the Geological Survey of India. The things on this scale are all smashed up, but I can only say that this is composed of rock mass ranging in age from Proterozoic to Cenozoic. We do not have any Archeans here in this landmass. Now, this is one of the sheets of the Seismotectonic Atlas of India, which I was one of the authors. The whole Indian subcontinent, including territories of Pakistan, Nepal, Bhutan, and some territory of Bangladesh also, are contained in 1:1 million sheets, which are numbering about 43 on 1 million scale. So this is one of the sheets which is covering the westernmost part of the Himalaya, and you can see we have got this is the syntaxial band, western syntaxial band. The frontal part of which is known as the Kashmir Hazara syntaxis or the Jhelum reentrant, and it has got a very complex sort of geological and tectonic setup. We have got the major geographic elements like Hindu Kush mountain range, Pamir plateau, Karakoram range, Nanga Parbat, Pir Panjal, and so on. And the major drainages here are Indus and Jhelum river. Then we have got tectonic elements like the Great Karakoram range, Kohistan Arc, Peshawar and Kashmir basins, then Kotwar plateau, and the Salt range, and the frontal part of the Himalaya. And the structural elements which are present in this particular sheet are the main Karakoram thrust, which towards its eastern extension is referred to as the Bengong suture. Then we have got the main mantle thrust, which is also known as the Indus-Sanko suture. Then we have got the main boundary thrust, the Jhelum fault, and so on. These are the Indo-Gangetic plains, which are thickly populated. And any hazard which is occurring in the Himalaya has got a direct bearing and influence on this region. This is the easternmost sheet, This includes the Uttarakhand Himalaya as well as of course the western margin of Nepal. And you can see here we have got tectonic elements like the Karakoram fault, the Itasucher, the Martoli thrust, the main central thrust, and the main boundary fault. Here, one interesting point that I would like to mention here is that most of the seismicity is concentrated along the trace of the main central thrust here. And coincidentally, all the geothermal springs are also located around the trace of Kashmir of this main central thrust. And it may not be a coincidence. Means why this association of thermal springs with high order of seismicity is existing. So it has got, you can say, it may not be one-to-one relationship, but definitely some genetic relationship. I am not going into the details of this. Now this is the GPS vector map. You can see these are the different vectors of GPS measurement. The eastern part and of the order of 10 to 14 millimeters per year in the western part. I'll come into the details of this. This is again the Himalayan arc, and as you can see, this is of the order of 10 to 14 millimeters per year in the northwestern sector. So a lot of strain is accumulating because of this convergence. Now I'm coming to the western syntaxis part. I'll give you some brief about it. We have got a record of about 940 seismic events in this segment of the Himalaya, the westernmost segment of the Himalaya. You can say the Western Himalaya has got predominantly thrust type of mechanism. The Karakoram range has got strike slip mechanism. The Salt range again has got strike slip and predominantly thrust type mechanism. The Indus-Kohistan arc has got a normal type of deformation, means extensional tectonics is in vogue there, and so on. Now, if you come to the upper part, means Kohistan and Pamir and Hindu Kush range, it has got a very complex compressional system of stresses, and here you have got accumulation of strain at much deeper level than in rest of the Himalaya, means of the order, the strain is concentrated at depths of 80 to 150 or 200 kilometers. That's why whatever earthquakes happen in the Hindu Kush range, though they are felt at far off places, they do not have much, you can say, damage potential. Now this is again the general map of Himalaya, where huge number of seismic activity has occurred, and I think this is quite unparalleled in the world in any orogenic system. As you can see, we have got these red dots are all +7 magnitude events that have occurred in the last 200 years. So this huge release of seismic energy in a very short span of 200 years for a mind is really a puzzle, and that's why we say that the Himalaya has got very high seismic hazard potential. Now this is the most accepted seismotectonic model proposed by various authors, and you can see here we have got these are, you can say, the peninsular regions or the Indian plate, which is subtracting below the Tethyan slab along a detachment surface, which is nothing but the upper surface of the Indian plate. And the red mark that I am showing is where the inflammation is there, or you can say the nucleation of high energy or high strain is taking place. And this green portion is where the aseismic creep is taking place, because this zone is ductile, so it is allowing the slabs to move over each other. But when we come to this portion, we have got, you can say, a fusion of ductile and brittle zones. So a lot of strain is accumulating here, and this is where most of the seismicity in the Himalayas is concentrated, say at depths of 10 to 20 kilometers. And coincidentally, this is lying just below, you can say, the MCT. So MCT is not giving rise to the earthquakes, but beneath it, you have got concentration of seismic activity. You can say these are the lesser Himalaya, these are the higher Himalaya. So at the junction of these two different geographic entities, we have got concentration of seismicity. Now I've tried to explain it with the help of a simpler model. These are the, you can say, this is Garhwal block, this is Kumaon block, and this is the detachment surface, and the major nucleation of strain buildup is, so if you take, you can say the Kali Valley, that the Hachula region, we have got preponderance of earthquakes. If you move further west, that is in Chamoli region, in Uttarkashi region, and further west in the Ravi. So where these river courses are following these deep-seated transverse faults, and wherever these are intersecting with the detachment surface, we have got higher strain buildup, and these are the locales where major earthquakes are occurring. Now I will take some specific examples of earthquakes so that the things are clearer to you. In the northwest Himalaya, first this is the 1885 earthquake of 30th May. It happened in the Kashmir Valley. There were some 3,000 fatalities. You can imagine that at that time the population density was much lower, and the epicentral intensity was measured as 1 on the Mallet scale, means it equivalent to about, you can say, 9 on the modified Mercalli scale or MSK scale. Now I'll go a bit longer on this 8 October 2005 Muzaffarabad earthquake, because it has been documented very well, both in the Indian part and in the Pakistan part, and some 87,000 fatalities were there, some 1,200 on the Indian side, rest on the Pakistan side. And these are some of the photographs, and this is the epicenter, you can say. This is Kashmir Valley, we are talking about China. So this is what I want to draw, that if a flood situation is there, if an earthquake situation is there, it is not only the involvement of one country, it is the involvement of various countries which are affected. So it has to be an integrated exercise, an integrated study. Now these are the isoseismals. You can say this is the Balakot region, the epicenter where the intensity was of the order of 10. And if you compare it with this Gorkha earthquake, there the epicentral intensity was of the order of 9, so a notch higher up above that. And it has got a very severe, you can say, elongation of isoseismals. So these isoseismal, longer axis of the isoseismals gives a very good idea of the seismogenic rupture, how and where it has taken place. Now these are some of the damage photographs, and here I want to refer to this. You can see these are the weak stone masonry walls packed in mud mortar, and this is the very usual type of construction throughout the Himalaya in the rural sector, whether it is India, whether it is Nepal, not in the eastern Himalaya, where we have got a different building typology. And under the dynamic load, you can say they behave very poorly. So this is one aspect which has to be looked after by the designers, the engineers, that how to make our structures safer in rural areas. This is damage in Muzaffarabad, means the stilted structures. The soft story fail invariably. We have seen it in case of Gujarat. We have seen it in case of number of cases in the Himalayan earthquakes. So either it has to be properly designed or it has to be dispensed with, means these stilted structures. Of course, the intensity was very high in where we are seeing, and these are the huge number of co-seismic sites. Now this is one example of Margala Towers, Islamabad. Here the seismic intensity was not very large, of the order of 6, but you can see the collapse of this 19-story building. So some inherent defect must be there, either in the design or in the construction practices. Otherwise, this building has no reason to fall. You can see that all the adjoining buildings are intact. So this aspect has to be looked after by all the structural engineers. And this is the damage in intensity 8 in Afghanistan. And these are again the very weak type of structures. Neelam Valley, can see the number of co-seismic landslides. So one point I want to emphasize here, and I'll elaborate it in my concluding part. Then this is one thing which most of the designers do not look into, means how the slopes will behave when a major earthquake occurs. And this has got a lot of direct relevance for the safety of the people. Now this is the 1905 Kangla earthquake. This was again investigated by the Geological Survey of India. And this is the isoseismal map. It has got, you can say, the twin epicentral areas, one in Kangla Valley, another in Dehradun Valley, of different intensities. And these are some of the photographs which are taken from the GSI records. And this is the, you can say, the grade 5 damage that occurred, means total collapse of structures. And huge number of landslides, some of which blocked the courses of rivers, and they were impounded temporarily, though no major flash floods occurred. And an exercise was done by the National Disaster Management in India that if a similar earthquake, now that earthquake of 1905 killed some 20,000 people, and this occurred at morning hours when most of the people were awake. But if such a situation, if such an earthquake is to repeat, you can say in the same seismotectonic domain, in this, what will be the situation here? This means taking into cognizance the present population density, the present housing density. Now some startling figures have come out. This is the, you can say, the hypothetical 8 magnitude earthquake. And if this earthquake occurs, say at dead of night, the casualty figures would go up to 900,000. This is a colossal figure, and all of us should be worried about it. Now this is something which is quite improbable. See, what is the history of 9 magnitude or 9+ magnitude earthquakes throughout the world? Some 9 or 10 events have been recorded, and all of these have occurred in the oceanic region, where you have got large length of faults, and there is a, you can say, almost a one-to-one relationship between the fault length and the size of the earthquake.
Dr. Pandey, could you...
5 minutes? Yes. Right. I'll finish it in 5 minutes. So if such a situation occurs, what would be? So in the continental mass, so far no earthquake more than 8 has been recorded so far. So this is one thing which we can say, with some background, that we will not expect a 9 magnitude earthquake. So in the Himalayan region, what we are taking for our seismic hazard analysis, and moment magnitude of 8.5. Sorry, this is the last one. This is the PSHA map of Northwest Himalaya for a return period of 2,475 years. That is the maximum credible earthquake condition. And here we can see the maximum acceleration of the order of 0.64 G is recorded in the Kangla region, and the lowest is of the order of about, say, 0.15 G. That is in the Indo-Gangetic plain. So this is the range of accelerations. And when we have to design, say, a specialized structure like a large dam or so, we have to do some site-specific studies. And there are some very specific guidelines how to design structures like that. Now I think I'm coming to the last slide. This is a figure that I have taken from the vulnerability atlas. And I'll go to the last line here. In the 3 provinces of India, that is Jammu and Kashmir, Himachal Pradesh and Uttarakhand adjoining Nepal, we have got a total area of 331,000 square kilometers. We have got a population of, say, 29.4 million people living here. We have got some 9.9 million housing units, and here we have recorded some 1,310 seismic events of the order of 4 and above, some 379 of more than 5, and 73 seismic events of equal to or more than 6. Means these are the damaging events that have occurred in the last 200 years or so. Now, I was studying the data of Uttarakhand. Here the population as well as the number of houses are increasing at the rate of 1.5 houses per year. And this is quite, and if you compare it for the 2001 and 2011 census data, the rural constructions earlier were 70% of type A, means the poor structures. Now in 2011 census, they have become only 18%. And most of the construction activity presently has resolved to construction of type B structures, means brick structures with some reinforcement. So this is a welcome change, and I think this change will come in the region of Nepal also, where the safer construction practices would be adopted. And lastly, these are some of the concluding points. The groundwater changes are very significant, and the seismic changes that are taking place underneath have got a direct bearing, and this can be used for some sort of precursor studies. Then co-seismic slow failures. Now, so far, I have seen the records that there are hardly any casualties because of seismic failures, co-seismic failures. But the situation may not be so in future, because all sorts of constructions are taking place at all sorts of places, irrespective of whether they are below slope, vulnerable slope, or so on. So, in future earthquakes, this aspect has to be looked after by the planners. In the built environment, I have already said, rehabilitation measures. I found in 2015 Nepal had a very robust, we can say, rehabilitation practice. Means aids were coming from different organizations, NGOs, countries, and so on. And they were getting pulled up at one place, and it was the government which was distributing to far off places. It is not so, at least I have seen in 2 of the earthquakes in India. Means the private organizations, the NGOs, they are given the task of supplying it to the affected villages. So most of the villages which are located along the roadside, easily accessible, receive much larger amount of aid. But the villages which are far from the road do not receive anything. So this system has to be very robust, and I think the governments have to play a very role. And capacity building means the ambassadors of revolutionizing the built environment in rural sector are the masons. So they have to be properly trained by really trained personnel, so that they adopt the best practices for making the structures seismically safe. Thank you very much.
Thank you for a very interesting presentation. Now, any question and comment? We have 2 questions.
I am Adab Singh Mara from Nepal Electricity Authority. First of all, I would like to give a lot of thanks, Dr. Pandey, for presenting your nice and too much informative keynotes. About that, I have one curiosity questions. About the seismicity, what type of problem will be found in the seismicity? What type of problem will be found in the seismicity after the completion of high reservoir dam? That the seismic area, like in the India-Nepal border, in the far western Nepal, 3 mega projects are proposed, like the Tisapani hydroelectric project, 10,000 megawatt, and West Seti 750 megawatt, and Pancheshwar also 6,000 megawatt project. Dhauliganga already existing, and Goriganga also, I think, and so many other projects are going to be built up. And if suppose we have dam height only average about 200 meters, then there will be the 20 megapascal will be stress area. And what will be the effect of it there?
I think I got your first question very correctly, and that is, I think, pertaining to reservoir-triggered seismicity. A lot of studies have been done in India also, particularly for the Himalayan region. And it is seen that the reservoir-triggered seismicity means the creation of impoundment causes a lot of stresses, and whether that will trigger an earthquake or not. So it has been found that earthquakes, which are, you can say, where the displacement takes place in the normal fashion, you can say in the extensional stress environment, only those give rise to the reservoir triggered earthquakes. Secondly, the Indian seismicity has to be of moderate or low level, as we have seen in case of Koina. And if the Indian seismicity is of very high order, like in the Himalayas, we do not expect any reservoir triggered earthquake. So as far as this aspect is concerned, most of our dams are safe, means they will not experience any enhanced seismicity, but for which they have been designed.
Thank you. It's time for move to the next presentation. Thank you very much.
From the side of Taranidhi Bhattrai, I feel proud to introduce Professor Dr. Taranidhi Bhattrai. Professor Dr. Taranidhi Bhattrai is the former head of the Department of Geology, Trichanda campus, Tribhuvan University, Nepal. Currently, he is a coordinator of MSc Engineering Geology program at the same department. He is also serving as a member of the steering committee and apex body of the National Reconstruction Authority, constituted to handle all the issues related to Gorkha earthquake 2015. He has over 25 years of teaching and research experiences, in addition to publishing books and contributing a book chapters. He has published about 75 articles in technical journals, proceedings, and edited volumes. He has served as a member of the National Nepal government's delegation to UNFCCC conferences and other high-level climate change meetings. He undertook several international joint collaborative research initiatives in the field of engineering geology, natural hazard management, and solid waste management, intercity transport, climate change, and sustainable development. He has carried out engineering geological investigation for several civil engineering projects in Nepal. He also served as the convener of the 8th Nepal Geological Congress, Geosciences in National Development and Disaster Management, held on November 27-29, 2016 in Kathmandu. Dr. Bhattrai obtained his master's degree in geology from Tribhuvan University, a PG diploma in engineering geology from ITC Netherlands, and a PhD in engineering geology from Kyushu University. I invite Professor Dr. Taranidhi Bhattrai to present his presentation title is Engineering Geological Approaches Adapted in Reconstruction and Relocation of the Damaged Settlements in the aftermath of 2015 Gorkha earthquakes. Co-authors are Stephen Richard Reville and Kamal Kimire. Welcome, Dr. Bhattrai.
Thank you, Dr. Bajulil. Respected Chair. This is a step forward to come to engineering geologist community to work together to solve the problem of reconstruction and relocation of our country. So, as my colleague already introduced, we have two more authors. Stephen, he also gave one presentation yesterday, and Kamal Kimire. So basically, I will be talking here just to recall what was the situation immediately after the earthquake in our settlement and how our government responded to the people's concern. And then I will also shed some light on the establishment of National Reconstruction Authority, which is the sole agency, sole government apex body responsible for the reconstruction. I will also show you the final results, and I will discuss what to do in the days to come as a concluding remarks. Now I request you just look at the photograph over there and imagine yourself, you are the resident of that settlement, that village. And imagine the time when earthquake occurred. During the earthquake, landslide occurred, we all know. And after the major earthquake, we have a lot of aftershock. And if you look all around your village, there were terrible landslides, very big surface ruptures. And those ruptures were sometimes extending day by day. And people started feeling that there might be another landslide as aftershock was coming and coming. At the same time, at certain location, the drinking water source, in some cases it is completely dried up. In other cases, discharge was gradually decreasing. In other cases, suddenly discharge increases. Particularly when discharge was decreasing and drying up, people were very much concerned. So people started conveying their concern to the local body in a district headquarters, and district headquarters were reporting the case to the Ministry of Home Affairs, and Ministry of Home Affairs itself was not sure what to do and what is not to do. Everywhere same concern was there. So the first and government's immediate initiative was to conduct geological assessment under the leadership of Department of Mines and Geology. We say rapid geological assessment. Whoever geologists were available in the country, those people were mobilized under the leadership of DMG, and based on their recommendation as well as report sent from district headquarters, government decided 475 settlements as the most vulnerable settlements, and the whole village has to be shifted as early as possible. In fact, 193 communities were immediately shifted, and for the rest, there was a plan from government, but as time spent, monsoon also arrived, but landslide did not occur to the extent it was expected. And this situation was there in one hand. On the other hand, government constituted National Reconstruction Authority, which was given mandate to formulate policy and arrange fund for the reconstruction. All the administrative staff for NRA are to be provided by the government. It means NRA does not have its own staff, fully dependent on government. And then another important part was policy level decision has to be made by NRA, but implementation has to be done by government concerned department. So very close relationship was needed to complete this task. NRA issued a public notice advising people not to start any reconstruction at the 475 vulnerable settlements. This situation created a tremendous pressure on NRA to justify its decision on the basis of scientific information which was lacking at that time. In fact, what had happened is, when landslide did not occur in that monsoon, people started going back to their native village. But NRA said, don't construct your damaged building. And people were unhappy, and they started asking, why should not we reconstruct our building? And of course, government decided it is a vulnerable one, but there was not sufficient information to say that the decision was based on science. So there was a tremendous pressure, and finally NRA accepted people's suggestion to conduct further geological study to make a science-based decision, but it was not clear which government department is responsible for this important task. Because NRA itself does not do anything. It may make a policy just saying that investigation is required. So investigation has to be done by government agency. But it was not clear who will conduct that part yet. So what we did is, we tried to understand the mandate of the government department, and at that time we came to know there are 3 departments belonging to 3 different ministries. One is the Department of Mines and Geology, who already conducted rapid geological survey immediately after the earthquake. The other one is Department of Water-Induced Disaster Management, which is mainly responsible to control deep-seated landslide. And the other one is Department of Soil Conservation and Watershed Management, whose mandate was to control shallow-seated soil type of landslide, and particularly in collaboration with local communities. So those 3 organizations were there, but these last 2 organizations unanimously requested that although mandate is with us, but we do not have enough number of geologists, so we request Department of Mines and Geology to conduct the survey. Their mandate was with them, but they transferred it to the DMG, and DMG also accepted at that time. And also later, DMG took the responsibility and investigated 131 settlements, but did not complete all the settlements. At that time, DMG reported they also don't have enough number of geologists. They have to work with their regular work, heavily loaded, so we don't have extra geologists to conduct NRA's responsibility. Then we left with no option to take the responsibility by ourselves. So NRA took the responsibility to complete the rest of the settlement's investigation. So what NRA decided is to conduct geological, engineering geological and geotechnical studies to ensure the safety of the communities against geohazards before reconstruction starts. And a study is to be conducted covering all the vulnerable settlements with an option of extending it in other communities based on need. So one point very important here, those 475 vulnerable settlements, the data was already with Ministry of Home Affairs. Later we came to know that there were many cases which were not reported to the government authority. And when this information was public, then people started reporting that we also left our village, we also left our community, so it has also to be included in the list and do the job. And at that case, because of our mandate, I mean NRA's mandate, we accepted that. But again, question was how to do it. NRA also does not have geologists. NRA does not have any technical guideline. NRA does not have any experience of conducting these sort of things. It was again tremendous pressure. What to do? Then NRA formed a technical committee coordinated by a member of the NRA steering committee. In fact, that was me. And it was extremely difficult for me as well what to do now. So we thought whatever knowledge available in our country in government system, let us utilize it. So the committee was constituted having a representative from Department of Mines and Geology, also from Department of Water-Induced Disaster Management, also from Department of Soil Conservation and Watershed Management, also from Nepal Geological Society, also from Nepal Geotechnical Society, and there was a provision to invite experts from different sectors to take their advices. And we discussed about the situation. We have a very huge number of settlements and we have limited time and how to conduct the investigation. So the mandate given to the technical committee was to develop technical guidelines required for the investigation and conduct geotechnical investigation of all those vulnerable settlements and classify those settlements into those 3 categories. Category first, this is sites having geohazards which can be managed by communities themselves. It means there is no big problem. Reconstruction can be started anytime. And category 2, sites having geohazards which can be managed by applying appropriate engineering countermeasures for which government support is required. So in this case, communities surrounding can be stabilized, but government support is required. Community cannot do it. That was second category. And third category, sites having geohazards which are extremely difficult to control or economically not feasible. In fact, settlement belonging to category 3 has to be moved in a safer side. So that was the mandate given to the committee. And then, as I mentioned before, considering the available knowledge available with government departments and universities and professional societies, we took several meetings and we developed investigation guideline, and in the guideline, geological, hydrogeological, geomorphological, engineering, geological, geotechnical, and pertinent social parameters were taken into consideration. And one of the difficult part at that time was, since we were working with different government departments, and their working methodology was not exactly the same. So it was very difficult to convince those professionals to come to a single consensus technical guideline. But somehow we did it. And then we also recommended that just investigation by a geologist is not sufficient. The team should be led by geologists. There should be 2 more members representing water-induced disaster management department and soil conservation department. That provision was there because implementation part was those departments. So if we do not include their part, their representation, it will be difficult for us implementation. That is why the investigation team was constituted 3 people led by geologists. And again, when we complete the team and when we talk with those team members, they very honestly told us, like many of us, they also told us they studied landslide in their classroom. They scored very good marks as well. But this is for the first time they were dealing earthquake triggered landslide in the real ground reality. And they were mandated to make a decision for which they were hesitant. And that was very realistic point as well. So we decided to have a training. In a way, they feel comfortable to work in that environment. So we also conducted training, not only in-house training, took them to the site, showed them to the landslide, and all the instructions were given. We also tested in some cases, and when we realized that they can work independently with the level of our expectation, then NRA finally decided to mobilize the team. But again, there was another big problem. Monsoon was approaching. We have only 2 or 3 months, and we have to cover nearly 500 above settlements, and we decided to constitute something like 40 teams, but there were no geologists. We tried each and everywhere, no geologists. Finally, hardly 10 or 15 geologists came to us, and I thank them. Many of them personally told me, although I have a lot of things to do, this is an important time to contribute for my nation and for my fathers, mothers, and sisters, all the Nepalese people. I will give you 1 month time, not much more than, just 1 month. We were happy with that as well. So we mobilized with sometimes 10 and sometimes 15 teams. They really worked very hard. I really appreciate. So this is something like we already provided them technical guideline and also informed them how to fill it up and where you have to make observation. All those sort of things were taught very clearly. So this is just to let you know one form only. and also ask them what was the situation before the earthquake, what happened during the earthquake, and what exactly happening right now. Those sort of information were also requested to collect. And then basically data interpretation part was qualitative, not quantitative. So this is just an example. If you look at the photograph over there are two villages. Those two villages were also listed as vulnerable settlement. And when our team investigated or went to that site, they came to know that all the building collapse was not because of the geological causes, not because of any landslide, not because of ground surface rupture, not because of liquefaction. So only because of structural failure, their building was only over there. So we consider those are category 1 settlement, where reconstruction can be started anytime. If there is some very simple type of things, we will just give some sort of training to the local communities and they will manage themselves. So that is one example of category 1. In case of category 2, for example, just look at the photograph over there. In fact, this debris flow took place not during the earthquake. It is during the monsoon immediately after the earthquake, and one building partly damaged over there. So our survey team investigated and came to know that there is no more sediment on the upstream side to slide down in the days to come. So their recommendation is, if we can control this gully on the side, reconstruction can be possible. Only the thing is, the controlling of the gully part should be provided support from the government. So this is category 2 settlement, just one example. Okay, so category 3 settlement, please look at the photograph again. There is a village, you may not see very over here. So what exactly happening over here is, this landslide, these all landslides were triggered during the earthquake, and there are cracks, huge cracks here, several huge cracks are also there. So what our team...
To conclude the talk, and very sorry for interruption.
So our team concluded, since this is a very difficult job, there is a river down over there and very long landslide, and these cracks are also very severe type of cracks and cannot be controlled so easily, or it is, if it is possible, it is really costly, and if we compare the cost of moving the village or applying the countermeasures, the moving the village would be the better one. That is why they put it as a category 3. So the final result of this investigation is, until now, 730 settlements were investigated, and the final result is category 1, 327 settlements, category 2, 213 settlements, and category 3, 190 settlements. And a further 200 settlements are still being investigated, with the aim of completing the survey by the end of 2017. So all the investigation will be completed very soon. Now I will just tell you about the result implementation arrangement. So category 2 arrangement, as I mentioned before, applying the countermeasures part is a government's department responsibility, and here Department of Water-Induced Disaster Management and Department of Soil Conservation and Watershed Management are responsible. We already informed them to do the job. And category 3 settlements job, this is the mandate with NRA, where we have to find safer settlement for shifting those vulnerable villages or villages. Now we have some challenges. When we talk about category settlement, again with these two organizations, they are extremely busy with their regular work. They have budgetary constraints, and bureaucracy is something very difficult to deal with this budget type of things. And not enough human resources. In fact, particularly geologists are not much with them. And one of the very severe cases, sometimes NRA bring officer in NRA and provide training, and when those people go back to their department, they will transfer to the another department. So department is with no export at all. That is why NRA work is not getting high priority. It is at least priority. And until now, technical guideline for countermeasures identification and implementation is still lacking. In case of category third, it belongs to the NRA. We are still working on it. There is also a very difficult task, is how to find safer site is a very difficult task. Ours is a mountainous country. Wherever we go, there is rock, rock, and rock. And constructing a building by local people at the rock slope is extremely difficult. And what we are thinking now, way forward, is considering those category 2 settlement, NRA itself is planning to develop 5 model sites. And those sites will probably include one rock fall site, another rock slide site, further another soil slide site, and creeping and river bank cutting site. We are considering 5 sites to develop as a model site, and during developing those sites as a model, we will also develop technical guidelines and all the relevant documentation so that it will be easy for concerned department to conduct their job. And for category 3 settlement, NRA is developing a methodology to select safer site for reconstruction, and also thinking if early warning system or monitoring can help to allow the people to stay on the same place. If it would, it will be very easier for us. So the final concluding remarks is input from engineering geologists has been mandated by many of NRA activities. Council of Ministers has clearly even mandated that only geologists can make a recommendation for 2 things. One, to say that the site is safe and reconstruction is possible, geologist has to give an approval. Second, those categories site 2, after applying appropriate countermeasures, again geologist has to say now site is safe and reconstruction can be proceeded. So that mandate is with geologists and engineering geologists. It has given us an opportunity to work, but there is a pressure again how to do it. So in this community, I am here just to request for a joint collaborative research, and where we can focus our idea is, this is not limited, just example, low cost and long lasting countermeasures, landslide early warning system manageable by local communities, and also some sort of site investigation technique in vulnerable steep slopes. We have a very huge rock slide where it is very difficult to go by walking, and we need some sort of technique where we can have site investigation data. And also we have opportunity for technology transfer and also for developing new methodology, for which developing residential area in steep rock slope. Until now we don't have any technology, we don't know how to do that. And also I did not mention before, but our drying out spring are still there. We have to rehabilitate them. So we would like to work with you because you have a lot of experience and lot of technology as well. So that is what I would like to convey here. And my part is just to let you know where we are and how we are planning to go. Now your part is to give us a helping hand and help us to make our reconstruction attempt successful. Thank you very much.
Being limited by the availability of resources of geologists, my question is, could you bring them from outside Nepal, firstly? Secondly, is there any such thing as engineering geologists without frontiers that could be provided to this kind of disaster when it happens again? And would it be an idea to actually create that kind of organisation? Thank you.
Thank you for your kindness and generous suggestion. One of the important part why geologists are lacking in our country right now is, of course, we are having geology graduates each year, something like 30 or 40, but majority of them are going abroad. That is why we don't have right now. Something like 40 engineering geologists are to be graduated very soon after 6 months. So we are expecting they will also help us. And at the same time, I noted down your idea of to bringing geologists from abroad. And if we make a decision on that, I will certainly contact you. Thank you very much, sir.
I would like to welcome Dr. Gata.
Thank you, Dr. Pajulet. Good afternoon. This is not a technical talk, but I am sure at the end of my talk you will be ready, planning for a mega conference that is going to be held in India and also in the adjoining countries like those are the co-host countries, Nepal, Bangladesh, Pakistan and Sri Lanka. So I am from the Secretariat, which is situated at New Delhi, and the conference dates are 2 to 8 March 2020 in Delhi. Going into the depth of the preparations, I would just like to mention here that IGCs are actually held under the scientific forum of International Union of Geological Sciences, and it has a long legacy starting in 1878. Until date, 35 sessions have been held all over the world, and the whole process happens through international breeding. And India won the bid in 2012 in Brisbane. We have our appropriate authority in our host country who appoints the preparatory committee or the local organizing committee, and we report to the International Geological Congress Committee, which is actually operating under IUGS. Now, if you look at the dimension of IGC, it's very huge, and over the years, the participation of IGC till 2004 had increased quite a lot. In the last IGC, their participation had gone down, but it's not a matter of worry for us. I'll tell you why. And I'm also happy to announce, because Dr. Scott is here and we had interacted during 35th IGC, IAEG and IGC are closely associated. If I'm not wrong, then this IAEG was born during 1964, during the 22nd IGC, which was 22nd IGC that was held in India, and that was the first IGC in Asia. The theme for IGC is Geosciences, the basic sciences for a sustainable future. The deliberations that you are having here closely is associated with the main theme of 36th IGC. And you are, as you know, that the subcontinent presents diverse geological heritage and offers opportunities for the development of geosciences. Our Congress will truly reflect an inclusive spirit and has adopted the model of science for all and not for profit. And we have a vibrant GeoHost program. That means a lot of supported candidates will be participating in the Congress. The important part is 36th IGC is a government-supported program, and two ministries have joined hands together, that is Ministry of Mines. I'm representing Geological Survey of India under the Ministry of Mines and Ministry of Earth Sciences. And it is supported by all the Indian National Science Academy and all the science academies of co-host countries. I don't have to go into detail of it, but yes, Indian subcontinent presents, it has a invaluable geological records from Archean to the Quaternary, from mighty Himalayas to the delightful valleys. It has expansive deserts to meandering rivers. It has vast oceans to seas, spewing volcanoes, and this all attests to the interplay of diverse geological forces and climatic implications. India has already notified 32 geoheritage sites, and more are being added to the number. So as I have said, these are the main funding bodies for the Ministry of Mines and Ministry of Earth Sciences. Geological Survey is the nodal organization, and it is being supported by all the national science academies from India, Bangladesh, Pakistan, Nepal, and Sri Lanka. So this is the venue, that is in India Expo Mart Limited, which is located at National Capital Region of Delhi. Venue is very vast. It has total area of 235,000 square meter, and it has more than 7,000 plus hotels or service apartments near to the venue. So initially we were actually planning for 6,000 plus delegates, but I will come to the end of my slide and I will show you that last Friday only the IAEG's bureau members, that is the President, Secretary General and the Treasurer, had visited India, and the kind of space available and the preparations that we could actually showcase, they are convinced that they are going to make this of this dimension, more than 8,000. So we are also enthused, and Nepal being the co-host country, we would also require your strong support, and I'm sure our coordinator from Nepal, Dr. Dahal, will be of great help. So thank you. So Delhi, during the march, it's very pleasant. Transportation is not an issue. We have modern metros, regular conference buses will be flying between the venue and the hotels. And we have a lot of heritage and museum sites which the delegates would be enjoying. Well connected, Delhi is very well connected. It has 60 airlines almost, and 400 international flights are flying every day. And we look forward to high attendance, and we are trying to make it a sort of very technically advanced kind of a program. So we will mostly go for e-posters and all, and we are looking forward to make landmark social events. And of course we will be having one professional conference organizer who can handle this bigger event to make it very attractive. So we expect that this 36th IGC would be a platform for knowledge and experience sharing, for professional networking, for developing international cooperation, increased academic production, and mind, these are all going to be monitored, and we will have one impact assessment workshop after the Congress is over. We will have first-hand information on latest technologies. IGCs are also forum for product launches, and we will have increased awareness of regional geology, public awareness of geology, increased, and these are some offshoots from this, that tourism revenue will also increase. Itself called 36th International Geological Congress, and our appropriate authority as per the statutes is chaired by Secretary Ministry of Mines and co-chaired by Secretary MOES and President INSA. There is 8-member executive committee who is looking into the affairs of IGC on day-to-day basis. Our president is Dr. V.P. Dimri, and co-president is Director General Geological Survey of India, Sri N. Kutub Rao, and our Secretary General is Dr. P.R. Golani. Both the President and Secretary General have recently taken over charge for this. We have followed a bottom-up process. Our preparations had never stopped. IGC provides us 8 years of preparation to organize a Congress of this dimension. So our our preparatory work began with the Secretariat, and we have different task groups formed to handle different aspects of the Congress. And GSI has also formed different regional cells to take care of the regional issues of 36 IGCs and acting as satellite center to the Secretariat. Now we are ready with our local organizing committee. So we have a science program committee which is chaired by Professor Talad Ahmed, who is Vice Chancellor of Jamia Millia University, New Delhi. Co-chair is Dr. P.R. Golani, who is also the Secretary General. Field trip subcommittee is co-chaired by Professor Somnath Dasgupta, again Jamia Millia University, Dr. N.R. Ramesh, who is the former Additional Director General GSI. The legacy subcommittee, who is taking care of a lot of publications during this event, is Dr. Fariduddin. Finance subcommittee is being looked after by A.K. Gupta, DYDG. Then the sponsorship subcommittee is chaired by Dr. Gopal Dhawan, who was a keynote speaker today morning itself. GEO subcommittee is Professor R. Shankar from Mangalore University. We have a volunteer program subcommittee who is chaired by Dr. A.L. Ramanathan, Jawaharlal Nehru University. We have an advisory subcommittee, and of course we have YES representative embedded into the local organizing committee. YES is the Young Earth Scientist Network, which is the forum for IUGS for the young scientists. And we are in the last leg of selecting the professional conference organizer. As I have already told, our preparations have never stopped, and our scientific program and the field trips have been generated through several number of brainstorming sessions which were held in different regions of India. We too had one international workshop. You can locate Dr. Dahal here, and from other co-host countries, people had united, and we tried to develop a program for the field trip, especially in the co-host countries. Our participation in various other forums. Our local organizing committee was officially announced during 35th International Geological Congress, which was held in South Africa. We had signed the Memorandum of Understanding with IUGS, under whose scientific aegis we are working, and to cover the uniqueness and diversity offered by the subcontinent. Till date, more than 50 field trips are identified in India, without considering the co-host countries. From other co-host countries also, and the neighboring countries, we have also got other field trips generated, like from Bangladesh we have 4 proposals, from Myanmar 5 proposals were there, from Nepal itself 5 were initially submitted and 3 more we have received up till now, and then from Sri Lanka we have got 1 traverse. The various publications have also been chalked out, and there are various other forums like One Geology or GGN, Global Geopark Network, wherein India is also participating under the aegis of IUGS. One of the biggest proposal that we have launched here in 36th IGC is its GeoHost program. Till date, no IGC have given this many GeoHost programs. I think the maximum was 565. So we are offering here 100 free registration, 100 hospitality, 1000 hospitality, and 1000 travel supports. Our youth GeoHost program for identifying 121 graduate students from IUGS adhering countries are also there. We will also have volunteers identified for this from different academic institutions. This is what I was talking about. This is the recently held meeting that we had with the IUGS delegates. You can see at the middle Professor Kuming Cheng, Professor Stanley, and Dr. Hiroshi Kitazato. And they are very, very impressed with the presentation and the preparations that are on also in the co-host countries. IGC, what we are planning, and going by the statistics of previous IGC, to have around 40 plus science themes and 40 plus parallel sessions, about 60 field trips. We have the facility to at least accommodate more than this, but this is something from the previous IGC statistics we have taken. 65 to 90 business meetings. This will include council meeting, general assembly, steering committee and other committee meetings, IGCP projects, technical group presentation, management group presentation, press conference, hour sessions, keynote, editorial board meetings, and other sessions. There are many social events also which the participants would be able to enjoy. And the Geo Expo, that is the exhibition, itself speaks about its dimension. We will have more than 250 plus booths. Here's the Congress timelines. We are slowly, we have just started that process, but within next 1 or 2 months, this information will be all available at www.36igc.org. So our first circular is being released very soon. You will have information on that. Sorry. Yeah, so second circular we will be having during September 2018. With these few words, I join my hands to welcome you all to India and the co-host countries. Thank you.
First, I would like to request Scott Bunn to give the program appreciation to Dr. Hasto Zuzeti. Okay, there we go. Yes, very good. I really enjoyed your talk. Thank you. Thank you, Mr. Friedman. Thank you. Thank you. it's your chair. Please start.
Good afternoon, everybody. So our first speaker today is Helen Reeves. I do know Helen, and Helen is the Director of Engineering, Geology and Infrastructure at the British Geological Survey, and she's going to speak. Well, I don't need to read it out. There it is. Helen, please.
Very much, Martin, and namaste. It's a great honour to be here just to share a project that we're just starting to work on at BGS with colleagues from around the world, actually. So I'm going to give you a quick insight into a project called Landslip. I apologise the title. My colleagues had a great debate over how to make an acronym out of this name, which wasn't hard, as you can see. So I'm just going to give you some of the background to the project. We've just started this project, so it's very much an overview of our aspirations and just a quick update on some of the progress we've made to date. It's a project that's going to last 4 years, and it's funded by a UK research institute organisation called the Natural Environment Research Centre and DFID, who are the UK's Overseas Development Aid Fund. And it's around a programme of work that DFID and NERC are developing for Science for Humanitarian Emergencies and Resilience, called SHEAR. We have a mixture of organisations, which is quite nice for this project, and you'll understand why. So we have academics from the UK, from King's University and Newcastle University, but then we have a number of, and also our Indian colleagues from Amrita University down the south of India. But then we have a number of government agencies, both within the UK and India, working together. So, for example, we have the UK Met Office, ourselves at the British Geological Survey, and also the Geological Survey of India. So, as I mentioned, Landslip is just starting. Although the programme started on the 1st of November, we've had a lot of logistical and administrative things and hoops to jump through. And we're just really starting to get going. But the vision, the overall vision for our project is very much how to design and create usable methodologies that can help us very much look at hydrologically triggered landslide events and try to develop methodologies that help us assess those in a robust way. There are 7 work packages which are interlinked to help us achieve our objectives. Overall, there's the coordination project, and then interlinked scientific work in progress will be also posted. So thank you very much for listening, and I'm happy to take any questions.
So I'm going to report an ongoing project. So when I finish and you are interested in joining us, you can just let me know, okay? And this is we call it Shenmu village in Taiwan. Okay, brief introduction. Taiwan is a small island, highest place 4,000 meters, and we have 73% land is slopland. And we have average more than 4 typhoons per year, and the accumulated rainfall for typhoon, well, the maximum is 3,000 millimeters for 5 days, so it's big. And for rainfall, just simple storm, we could have hourly rainfall greater than 150 millimeters per hour, okay? And the maximum annual rainfall easily exceeds 5,000. Now, using these photos, you can actually see a lot. For example, from September 10 to 24, within 2 weeks, you see, the accumulated material has been swapped away, and with a lot of tree trunks left, only 2 weeks. And for this place, you can easily see that within 10 days, there's a big debris flow event occurred. This place all wiped out, okay? And also you can see from the photo that we have a huge landslide area up there. But for this watershed,
there's no deep city landslide observed. So if your target is deep city landslide, you might get disappointed here. Now the basic information we have right now is the roadmap, the land usage, the watershed, GIS layers, and all the reports and papers for this area. And all the geologic map is in 1 to 5,000, and we have satellite photos over 20 years. For example, from satellite photos, you can identify, for example, this place. A lot of landslide. After 10 years, all the landslide almost recovered. So this subcreek will not be the main force of our monitoring.
It's quite evident the difference between in the previous one, you can just see the limit of the landslide. On the contrary, inside this representation, we are also able to recognize all the geomorphological features that characterize the landslide. So the same landslide, more or less in the same period, using different approach, at the end we didn't find a single result. So in this image you can see that the geometry of the final results is quite different. It's not that easy to understand using this representation. This one is better. So this is the benchmark. We also did a field survey, and we use both satellite imagery or in stereoscopic or monoscopic approach, and images come from UAV. Not so far from the performance of UAV, but this just if you consider the limit of the landslide. So what does it mean? It means that if you have to make a landslide mapping of a very large area, probably you can consider the satellite solution. As you can see in this frontal representation, the geomorphology of this area is very complex because it's not only a very simple rock wall.
His company is basically based in Chandigarh, Milliard Structural Solutions. If you're aware, Milliard Structural Solutions, it's a structure-based company. So he's there, and now I have started applying in Qatar also, in the teaching line.
के को हाम्रो सिम्पल थियो तस्बिर यहाँ त भिडियो यो रातो माटो चाहिँ कसरी एक्कासी देखा पर्यो भनेर हामीले सानो एउटा त्यो कोसिस गरेका थियौँ त्यसमा चाहिँ हामीले हेर्दाखेरि त्यहाँ पहिला डेब्री फ्लो भएर चाहिँ हो त्यो डेब्री फ्लो आइसके पछाडि त्यो डेब्री फ्लो केही इभेन्टको बेला तल खुरकोट एरियामा चाहिँ एउटा ह्युज ल्यान्डस्लाइड गएको भएर त्यहाँ ड्यामिङ गर्यो त्यो ड्यामिङको कारणले यहाँ माथि पनि त्यो पानी जमेपछि त्यहाँ सेडिमेन्टहरू डिपोजिट भएछ र त्यो सेडिमेन्टहरू पछि अक्सिडाइज भएर यो रातो माटो चाहिँ क्लियरली देखिएको छ अनि यसमा के छ भन्दा यो रातो माटो र त्यो डेब्री फ्लो जुन डेब्री फ्लोको डेब्रिसहरू छ हो त्यसको क्लियरली चाहिँ हामीले बाउन्ड्रीहरू देखाएको थियौँ फोटोमा चाहिँ अलिकति देखिएको रहेछ त्यही हो अब अनि यसको हामीले डिरेक्सन कताबाट फ्लो भयो यो डेब्री फ्लो भनेर गरेका थियौँ त्यसमा चाहिँ हामीले यो रोज डायग्राम बनाउँदा साउथ वेस्टतिर त्यसले डिरेक्सन देखायो
Face only. So we located to here, there, and see from here. This is a fresh one, but this is weather. Gradually changed. So we can easily estimate.
So here you have a glance of everything you can provide.
Thank you very much.
यो पुल यहाँ चाहिँ 1 महिनासम्म बन्द भएको थियो नि राजमार्ग यहाँ पर्छ यो चाहिँ हामीले अब पोलो बिमामा गर्न आफ्नो कुरा भएन डाटा सिट लिँदाखेरि होइन त्यही भएर यो चाहिँ हाम्रो चाहिँ यहाँ चाहिँ मोडल घाँचेर आयो तर त्यहाँ के भयो पहिरो भयो
There is one ridge and there is another ridge here, and between the two ridges there was a linear depression, but now filled with sediment, and there is a flat surface here. This slide shows the one example of the core of the boring,
and we have carbonish mud on the top of the core, and the carbonish mud gradually change to gray mud to down mud, and also the bottom of the core is orange mud with crust. Also we have tephra, and refractive index of volcanic glass in tephra indicates this tephra is correlated with KAH tephra in Japan, and age is 7,300 years ago. This blue line is the estimated top of the basement rock. So the interesting thing is sediment accumulated in this linear depression, wedge shape.
And for the empirical model of friction angle with the slope angle, there is a low correlation with only R² of 0.4711. The low correlation between the friction angle and slope angle can be attributed to the fact that the model is derived from the test results of 4 different cell classifications, which have, there is an improved model with a slope angle of greater than or equal to 27 degrees, represented by this equation in exponential series, and with R² of 0.903. Therefore, it is proposed that a constant friction angle will be carried. So for the validation of the model, another samples were taken from different sites, which is also a landslide prone area with the same geology from the study area. With a high R² of 0.984, the model is successfully validated, and the empirical models of fusion and friction angle with the slope angle demonstrated a good correlation and can be used to predict the spatial variation of the parameters in the area. And thank you for listening.
The table, classification table, serves the purpose to some extent, but not very definitive, because it is descriptive in nature, and therefore it is always good to have some index test values along with this classification, so that can substantiate such classification. And when we come to the classification of rock materials of these areas, those all are granitic rocks we considered. Here you can see that it is starting from grade 1 to grade 4, however there are some intermediate grades which were incorporated. There is a release of locked-in stasis within the quartz. So, although quartz itself doesn't get weathered or altered, it may have some more tracks which was not there if it is fresh. In this case, we try to do multiple impacts at a certain point, and the difference between the first and second impact gives a good indication of the weathering rates, and if the high impact hammer is used, that gives a better indication of weathering rate than the light hammer.
So these are the basic theory we will be depending on to actually deliver our project. So this is the geographical scale, scope and scale of our projects. So basically we will be targeting the Karnali Basin and also the Mahakali Basin, so we will be trying to develop a kind of regional scale landslide audio warning system in these basins, and also to actually test our community approach. We will be pinpointing some of the very key community areas, like we have like 4 or 5 different sites under this basin. So in this basin, in these areas, we'll be choosing 1 or 2 sites so that we can actually test our hypothesis, the community aspects. So how our approach in designing the citizen science component can actually complement this landslide reduction process. So the lead is the Imperial College London. Practical Action is it's a consortium partner, and so we have like a range of different scientists, like from physical science, from social science, and And the oak packages also, we have like the 4 different oak packages. So one oak package 1 is the hydrometeorology, 2 it's the all surface processes, and 3 basically focus on the citizen science and the participatory approach, and the 4th one is the impact oriented oak package, I said. So that's the polycentric reduction and the resilience building. So these are the 4 oak packages. They are involved in all the stages, not only in the like information collection only, but also in the information processing and also the information provisioning. So if we could involve all the actors or the vulnerable population in those areas, then obviously we'll have like a more impact. Thank you.
Part 1. Land-style monitoring is an efficient means of prediction of land-style's stability. Technology involving 3D laser scanning and remote sensing have been applied to facilitate land-style monitoring. In this study, a comprehensive information system for land-style monitoring is proposed. Its main functions include 3D visualization of basic engineering geological data, secure monitoring of the land-style. Land-style monitoring has always been important subject in the study of land-style, and many recent studies have been concluded on the related topics, but however have the following deficiencies. 1. Doesn't have a unified platform, and 3.2 data model. Data model have the system monitoring data were mainly obtained from monitoring instruments, including drilling incremental. This picture is all the proper information of borehole incremental measurement value.
The scheme consists of 5 steps, which are all carried out under the water level change condition. Each test will undergo 15 times water raising and dropping. First of all, here is the final test results, which show the different slopes, and we divided this into 4 control groups. Here is the first control group about different slope angle. You can see the slope with a bigger slope angle has a more violent collapse, and in the next comparison, this is the control group.
When I found the deformation, we put some new crack gauge at this area, high precision, high resolution, so we can do this work. Thank you very much.
Very happy that he's going to give the special lecture on this topic, and I request Ganesh to start this session. Now we are nearly in the time. You have to give small, brief information about the Professor Martin Kuslu, and then we start this lecture. Thank you.
Let me say a few words about Dr. Martin. Currently, he is Chief Editor of Bulletin of Engineering, Geology and Environment. He was a Director of Environmental and Hazards at British Geological Survey back in 2008. He was a member, and he served as a member in the Executive Committee of British Geological Survey in 2012. He has a very broad field of experience, and he has covered almost all aspects of the engineering geology and major parts of the geology as well. And he has over 40 years of experience in this field. So this is a great honor for the organizer that he is here, and it's a great opportunity. And he is a visiting honorary professor at of Engineering Geology at the University of Birmingham. He is Honorary Research Associate of British Geological Survey, and he has more than 160 papers, books, and articles published today. He received the Engineering Group of Award from Geological Geological Society of America in 1989. He is also a Glossop lecturer. In 2004, he got the Glossop medal. He has awarded with the E.B. Burwell Junior Award by Geological Society of America in 2006. And he was awarded with the Hans Klus Medal in 2010 by IAEG. So I would like to request Dr. Martin for your lecture.
This is a talk about writing a paper, okay? But before I actually start on the presentation, I've got a few introductory comments. And if I was telling you about how to give a lecture, you don't do what I am about to do, right? And that is read some stuff from bits of paper, all right? But I forgot about it, so I didn't have time to put it on my presentation. So I'm going to start. I mean, to those of us who have written more than 2 or 3 papers, it all seems fairly easy and straightforward. But like most other skills, it has to be learned. Very few people come to writing naturally. Many scientists begin their careers by writing technical reports, and these can be quite simple things, a record of laboratory work or site or field measurements, and then more sophisticated interpretation of that data. The factual reports provide a permanent record of measurements and observations, while interpretive reports give an explanation of why the data are what they are. So, a factual report might be a series of borehole logs, in situ or laboratory test results, while the interpretive report might say why the results vary, how that variation relates to lithostratigraphy, and so on. This lecture is intended to be for early career scientists and engineers who deal with ground-related problems, whether as researchers or practitioners. But there are different types of paper that you might look to publish. 3 basic types: a review paper, and these are often based on keynote lectures, and whilst many research students will do a literature review, what they produce isn't necessarily what one might call a review paper. Then there are case histories, usually based on a specific work at a specific site, engineering site, and then there are hypothesis-based research papers. A review paper brings together the knowledge and information gained over many years, usually covering a relatively narrow aspect of research. And usually there are very few new results or data. And what's being done is to give an overview of the particular subject. A case study looks at a particular problem encountered on site and indicates how that might be overcome and what lessons were learned. Sometimes a case study will cover failure And these are very useful, but rather few and far between, because most of us are not really prepared and may not be allowed contractually to discuss a failure. And obviously a hypothesis-based research paper essentially provides the outcome of the testing of a specific scientific hypothesis. For example, the hypothesis might say that the ABC clay formation is more susceptible to mass movement than the XYZ clay formation. And then factual data will be collected, analysed, etc., etc., and an interpretation carried out to prove whether that hypothesis is correct or not. So before beginning the main presentation, I just want to say that and acknowledge that this lecture was developed from something done by Nick Rengers, who is a past president of the IAEG. I've modified it, I've fiddled around with it, but to be honest with you, it's really his lecture, so I acknowledge that. Now, am I going to cause problems by that? Are you all right? Because you're filming this, aren't you? Yeah. Okay. So, what I'm trying to cover in this talk is communication issues, which I'll come on to, how to write, that seems a statement of the obvious, but we'll see. And then I want to talk about the structure of scientific papers. I'm not going to give you fixed rules, because I don't really think there are any. You may follow what I recommend or others recommend, but ultimately the style and the method that you adopt will be your own. And I'll give at the end of the presentation a few references that you can go to if you want to learn more. Right, let's get down to basics. Purpose of a scientific paper. It's to communicate new, original knowledge. And the intention is to allow others to use it, change it, disagree with it, and so on. So, we need to report what we're talking about, and these points are quite important, in an unbiased, clear, concrete, and coherent and logically structured way. If we don't do that, then the chances are that it'll be hard for people to understand what we've said. And do remember that this is not language specific. I'm talking in English, but what I'm saying applies to a paper, whatever the language. The exciting bit is doing the research, but just as important is properly reporting it and publishing it. And it's only in this way that you make a contribution to science. You can make an impact. Now, impact is a word that I loathe, detest, and hate, and it comes up whenever we're talking about research papers, journals, etc. Journals have an impact factor. Oh dear. That means that what happens is it's a metric, people compare the scores and get into all sorts of convolutions in trying to publish in the best. Who said the journal with the highest impact factor was the best? I better not go there. So I suppose what I'm saying is that it's not only about presenting your work to your fellow scientists. You're selling yourself, and how you write, and not what you write, but how you write, can have a big influence on what people think of your research. Well, I don't really want to talk about this slide because I've already said that I don't think much of the metrics, but the system is well developed. We all know approximately what it means, and there are probably as many different indices as there are days in the year. I mean, I discovered one in my last days of working when I tried to impress my director and told him about something or other, and he said, well, my Hirsch index is 30. And I thought, and he said, what's yours? And I said, I haven't got a clue, I've never heard of it. So, you know, I don't want to get into that really. But I do acknowledge that your employers, universities in particular, research centres, do take account of these metrics. And let's face it, research funding follows those that are judged the best. The question is whether these indices indicate the best. But anyway. I think another thing to remember is that you're not just writing for others in your narrow discipline. So I've given an example here, paper on debris flow development. It's not necessarily of interest only to applied earth scientists, but also to, for example, civil engineers, urban planners, emergency services, and decision makers, whether at a local level or a national level. So how you write and how you communicate your work it has to be clear and all the rest of it if these people are to stand a chance of understanding. So, to ensure that your paper will communicate effectively, you need to ask a few questions. One, who is my audience? And I don't mean I have chosen the best journal, I believe, in engineering geology to put my paper in, and therefore the readership of that journal is who my audience is. No, I want you to ask yourself, who is my audience? Who am I trying to inform and communicate with? And it may not always be other academics. Why am I writing the paper? What is my purpose? Now, it's okay to say I'm writing it because my supervisor has told me that I've got to publish at least one paper before I'll get. Okay? That's okay, but it's a bit sort of inward looking. So you need to think about why you're writing it. And what's the message? I think you should always try to think of what is the basic, simple message that you're trying to get over. Now, for most research papers, that's not so bad because you will have used a hypothesis to develop your research, so you are addressing the hypothesis. And what you're saying to the reader is, here's my hypothesis, and I've proved that it's correct, or proved that it's not correct. Look, so it needs to be thought about. Okay, so here are a few references on communication issues, but don't worry, this presentation appears on the website of the IAEG, so if you go on there, you'll be able to get these references. Okay, let's move on. How to write. Well, I've called this the standard approach, but it's that approach. Define the paper's content, write an outline, write a first draft, and then revise and polish. If only life was so easy. If only we could all just sit down and do it in that way. Because the standard approach doesn't always work for us as individuals. We're only just started to think about writing our first paper. And we're terrified, and we haven't got a clue how to begin or anything. So here's a few little suggestions. Ask yourself what the purpose of the paper is, and for whom the purpose is written. Ask yourself how you're going to achieve that purpose. And the main thing is to get ideas moving. So talk to colleagues. You don't have to, if you're a student, you don't have to talk to the supervisor or the staff. Just talk to your colleagues. Talk to anyone who will engage in a discussion with you. And make lists. When you've got a good idea, add it to a list. I mean, I've then said, take a rest, because you can't do this non-stop. You have to sort of have a brainstorming and then move away from it, then go back to it, and so on. Condense your ideas into a few short sentences, and then talk to somebody about it. And then, when you've had a little rest from it, read the outline again, and then begin to write a first draft. But what do you do when you can't start? I mean, it's traditionally called writer's block. But how do you get over writer's block? Well, there's some thoughts here. Don't be too self-critical. Don't have huge expectations of yourself. Just write down anything that vaguely relates to what you know you want to write. Doesn't matter whether it's coherent, you're making a start. You can always revise it later on. And you don't have to start at the beginning. In fact, I don't think starting at the beginning is a very good idea at all. I mean, traditionally, and you'll see this later, abstracts, for example, should be written last, and usually the introduction is not necessarily written first. So start in the middle, or wherever you like, it doesn't matter. It's about getting going. Describe the paper to someone, as I say, a colleague, a friend, and then ask them to make notes, record what you've said, because it's often easier to speak something than it is to write it down. So, and I think for many of you, you'll find the starting, the getting going, as the hardest bit, but you mustn't get obsessed with it. Just write something. Just get going. Do it in bits and shuffle them together. Anyway, so despite what I say, papers do have a formal, quite formal structure. Most of these, or some of these words, won't necessarily appear. Certainly introduction will, and certainly conclusions will, but the others may or may not. So what we have then is, at the start of a paper, title and authorship. Then the abstract, usually these days keywords, then into the main part of the paper, the introduction. Then a section that describes your materials, or it might be the geology or whatever, and the methods that you have used, the results that you've obtained, a discussion of the results, and then finally your conclusions, and then obviously your references. right. Title. The purpose is twofold, really. Attract your reader's attention, and then to identify your topic. Keep it short. There is nothing more certain to put off a potential reader than a title that is about 25 words long. So keep it short. 7 to 10 words is a good guide. Accurate. It should be accurate. It should be simple, and you should know what it says if you're reading it. You should know immediately what the paper is about. So it should be accurate, it should be simple, and it should be clear. Don't waffle on with sort of ambiguous, clever, pseudo-scientific stuff. Just make it clear. So here's an example. Study to determine landslide occurrence in Sichuan, or even landslide occurrence in Sichuan. You know where it is and you know what it's about. Or here's a slightly longer one, correlations between petrographic and geometrical properties of ophiolitic aggregates from Greece. Again, you know where it's talking about, you know what it's talking about, it's aggregates that are composed of ophiolites, and it's about petrography and geometrical properties, the shapes of particles. From what I can remember, these are actually real titles. For the authorship, you've got to follow what the journal tells you to do. But usually, you'd be giving your first name, your given name, and your family name, your postal address, your email address, and there may be more. But those are basically what are required by most journals. The abstract. It's disheartening to note that the abstract is often the only part of your paper that will ever be read. As you've been informed in the introduction, I'm the Editor-in-Chief of the Bulletin of Engineering, Geology and the Environment. Sorry, that's the advert over. And I have read, in the last 5.5 years, I have read almost 3,500 abstracts. I have not read 3,500 papers. I doubt if I've read 350 papers. It's probably more like 35 papers. So, you know, now I have a job to do as editor, which is why I don't read many of the papers, because I'm not interested in them. But, you know, it's the abstract that should tell me and you and the people you're writing for what your paper's about. I mean, people aren't being sort of nasty by only reading your abstract. It's just they read it, and it's terribly boring, so they don't read it anymore. Or they discover by reading it, it's not actually something they're interested in. It is the paper in miniature. So, the main points from the paper have to be included in the abstract. And you don't put citations in abstracts usually, or get into long-winded stuff about how and why you interpreted the data in the way you did. You've got 300 words, usually, no more, often less. Oh, and I said it before, it is written last. So, we've said that the abstract is the paper in miniature. And these figures here given for the main parts of the paper are only guidance, they're not absolute. Sorry, these are the bits from the main paper in the abstract. So roughly 20% as introduction, 25% methodology, 30% on results, and 25% on discussion and conclusions. And you can see that you don't get many words, all right? You get, for the methodology, you've got 70 to 80 words. It's a guide. It's not a fixed rule, but just bear that in mind. And as I said, usually it's 300 words, might be 250, rarely 200 or less. Keywords. Usually you're expected to do about 5 or so maximum, but they are important because if somebody's searching for papers on a certain topic, it's often the keywords that are used. So you need to ensure that the keywords are right and relevant to your paper so that people can find it. So, you know, I've made a point here about people doing literature reviews. If your keywords don't appeal to them, they're not going to look at your paper. So they need to be thought about and accurate. Okay, the introduction. Here are some of the things that we need to include in the introduction. A definition of the problem and a description of its importance. Well, in a sense, if you're a researcher, that's your hypothesis. You need to include your hypothesis because otherwise you're not stating what it is your research is actually about. Purpose and objectives of the research. Summary of existing knowledge through a literature review. And the questions to be answered by your research. So, you've stated your hypothesis. Well, what questions did you ask and then work with to prove or disprove your hypothesis? And something that might be forgotten, for case histories, please remember to tell us where your site is and about the site conditions in general. You'll be surprised how many people provide a quite detailed map of the location, and they call it a location map, and I've got no idea what country the site is based in. Well, I can work it out, but I don't want to have to work it out. So make sure you give adequate information. The literature review. Now, I've listed here some points about what the point or what the purpose of the literature review is. It's an inventory of existing knowledge, but you know, be careful because you could include rather more than you intended, and once you start moving away from the main subject, then you know you're not helping yourself. Of course, a literature review itself, where the paper is a literature review, you're likely to include a huge amount of existing knowledge. And I'll tell you a little secret. I was writing a review paper, and it had loads of references in. It had hundreds and hundreds of references in. And I got so fed up of searching references, I decided that my main objective was to get a reference where the first author began with every letter of the alphabet. So I wanted to have in somebody with the first author began with A, and somebody B, and somebody C, and so on. Unfortunately, I failed, and it wasn't over sort of oddball letters like Z or Q. It was more mundane things. I can't remember what they were, but there were 2 letters I didn't get. Anyway, it's what you do to amuse yourself when writing sometimes. So the literature review needs to, and this is an important point, it needs to relate your work to what others have done previously. So your work is being set in the context of their work. And the literature review, to an extent, justifies the research topic that you're talking about, the design of your research, and the methodology you have used. Because what you are pointing out is what hasn't been done previously. And rather than doing what I did in my review paper, only use references that are of real importance to your work. It is very easy to sort of bung loads of references in and think, aren't I clever? But I'm not sure, well, I don't think that's a good thing. They should think references that you have consulted and summarised or talked about need to be directly relevant to your work. Okay, introduction. Third. Some of the key questions you're seeking to talk about are listed here. What do we already know about the area that you're working in? And I don't mean the geographical area, I mean the field, the piece of research. What are the main issues, concepts? What are the existing theories or debates going on about this subject? And particularly, what's missing? What are the shortcomings? Are there inconsistencies in what other people have written? Are there gaps, therefore, in what's being done? And hence, what you can contribute to this particular area of science. You can't read everything, okay? Sometimes seems that you have, but you can't do it. So you do need to be selective, and you need to use the various indices and websites and so on to help you find the relevant things. I've suggested that you avoid just reading and actually underline things. It's okay if you're doing it on a downloaded paper online, but if you're still using the old-fashioned paper, don't underline in a library reference book. It is wonderful to, I mean, when you get to my age, you're not doing any active research, so the main way to get yourself published is to write historical things. It's great fun, and it involves sitting in library basements, looking at references from the 19th century and finding someone's been before you because they've underlined the key points. And it can be quite helpful. Anyway, so underline, highlight, whatever. Oh, and here is a first really key point. Don't plagiarize. What do I mean by that? You can't you can't steal what somebody else has written, put it in your paper and pretend that you wrote it. You can't do that. So there's only two ways around it. One is to summarize a point in your own words and then put the reference in, or you can take a phrase or a sentence or even a paragraph, but put it in quotation marks or whatever the equivalent is in your language, and so you make clear that it is a quotation from elsewhere and give the reference. Okay, the next section is broadly termed the methodology. What did you do to address your hypothesis, the scientific questions that you are asking? What equipment did you use, whether it's in the laboratory or on site in the field, and any other materials that you might have used. What measurement methods were used, and what methods of calculation did you use to analyse your data. Now, it's always a bit difficult about how much you write about these things, but I think in a moment it says, you know, you don't need to say an awful lot if you're using a standard method. Anyway, so you need to describe the approach that you used and describe and define the methods, and you'll see there that I've said that if using standard procedures or methods, it's sufficient usually to give reference, the reference for it. So if it was me and I was doing plasticity measurements, in saying the method that I use, I would simply say I use British Standard XYZ and the year, and that's enough. You don't need to describe that method. Only if you've invented a new method do you need to describe it in any detail. So the method thing is actually quite straightforward, the method section, because you know what you've done. You've been out on site, or in the field, or in the lab, or wherever, or sat in front of your laptop, and you've used kit, programs, whatever. So you know what you've done, so you have to tell us what you've done, what you've used. So it's often not too difficult to write that section. Results, now we're getting more into the meat of the paper. The data. Now, to me, these basic things are really quite important. Where, when, and how collected. You would be surprised, well, maybe some of you would, how many people don't actually tell you what they've used. I mean, I frequently, I get papers where somebody tells me that they've done all this testing on granite. Well, that is really unhelpful, because what sort of granite? What was its weathering condition? Where was it from? Usually that's not good enough for me. You present the data in a table, usually, or a series of tables. And I'll talk about appendices later. If you've got a lot of data, you may put it into appendices, but I've got some rules about appendices. So, you need to present the data, because if you don't present the reader with the data that you've used, how can they know the reliability of your interpretation? You then get into how you've gone about interpreting and analysing the data. This is simply to tell us what methods you've used. Statistical methods, whatever it happens to be. And you need to explain how you will be translating the results into information to solve your research question. Oh, it's some geophysical data. But basically, these are some results. That's all they are. They're results which you've chosen to present, because you will be using them to discuss later on. But here we have some more results. Two things plotted against each other, elevation and magnification factor, but it's results. And later you'll be looking at using that graph to explain why it supports your hypothesis or not. So these are examples of results. As I say, if you've got 100 plasticity data, you'll probably put, you might not know, you probably wouldn't put them in a table, but you need to think about tables, diagrams and so on. You're here in the process, in the discussion of answering that research question. That's what you're doing. You're going to discuss your data and so on to answer your research question. You refer back to the question or the questions in the introduction, and you provide answers and you explain how you got from the data to the answer. You need to consider the reliability of your data, the errors associated with it, the limitations, and particularly where your data contradict others. You disagree with others in your interpretation. And you may include in your discussion recommendations for further research. And in this section, you are allowed a little bit more freedom to float ideas. In other words, what I've put there is less objective. It's okay, as long as you can justify what you're saying in some sort of way, that's fine. So, opinions, speculation, to a degree, is all right. In your interpretation of your results, you'll want to compare them with others. And an honest interpretation would point out shortcomings not only of other researchers' work, but maybe shortcomings in your own work. But be careful, because if you go too far with that, you might end up getting your paper rejected. You do not introduce new results into the discussion. You need to discuss and point out why you think your results differ from other people's, particularly if there's quite a difference. Because if there is a difference between your results and somebody else's, other readers might think you've made a mistake, and it does happen. The last main section is the conclusions. These give the overall findings of your study, and it doesn't mean the last bit of the paper. They're really a series of statements which bring together the main points of what you've found. But it's not a summary. You're not summarising the rest of the paper. You're concluding, you're drawing out the main points that you believe your research shows. And the other point to be made is, do not, under any circumstances, introduce anything new in the conclusions that haven't been discussed earlier in the paper. And you don't include references either in the conclusions. Acknowledgements. Usually acknowledgements will be to people like those that funded your research, or colleagues who helped you but are not authors of the paper. So it's a thank you. But don't put in, I'm really grateful to my mum and dad for supporting me through what seemed to them like a lifetime of useless university study. Don't. If you want to do that, do it in your MSc dissertation or your PhD thesis. That's okay, I don't care. But don't do it in a published paper. All right? We've been through the main parts. This gives you a guide in the main part of the paper for how long each bit is. Introduction 20%, methodology 25%, results 40%, discussion and conclusions 15%. It's only a guide, it's not, you know, it will vary depending on what your research is, what you've got to talk about, but it's just a guide. The references. Right, as an editor, I'm obsessed with references. When I can get round to it, I will put on the website, for all the main conference proceedings, how you should quote a reference in a conference proceeding. Because I would like to bet that 70–80% of you do not know how to do it properly. Okay? Sorry, but it's true. It's an alphabetical list, usually. Sometimes I know it's numbered. You know, the first one you refer to is number 1, then number 2, number 3. But most journals, it's an alphabetical listing. And you use a standard format. Okay? And although there may be variations, most journals do it in the same way. Why do we have references? Well, I mentioned plagiarism earlier. Plagiarism is not allowed. You can't nick, steal, borrow, use the words of others without acknowledging them. It allows the reader to check the source, to read it themselves, to see if what you're saying, when you compare your data to somebody else's data, that it's okay. It helps provide justification for statements that you've made. And it safeguards you a bit against mistakes made by other authors. If you quote, or not quote, or use what somebody else has said, and it turns out that it's wrong, but you've made a reasonable attempt to write down what they've said, then you're in the clear. It was them who were in the wrong. Referenced, I've said, quotations, summaries, paraphrases, facts from references, and distinctive or authoritative ideas. And the criteria for referencing is that references that you provide should be clear, full details so somebody else can find it. They should be consistent, so you cite in the same way, and they should be correct. You'd be surprised how many people have never actually read the references they quote, and therefore they get them wrong because they've taken the reference from somebody else's paper. And the most common mistake is getting the page numbers wrong. But anyway, so that to me shows that you never read the reference in the first place. You're just adding references. Here's an example. I don't really want to go through these, but there's a format, and it's in here about how you should do it. So for a paper, it's the authors, the year of publication, the title, the journal title, the volume, the issue, and the range of pages. All of that. And there's some examples, and then conference proceedings, which you are collectively useless at quoting, authors, year of publication, paper title, because it's in a conference proceedings, names of the editors, please, proceedings of whatever, a location, the volume number, the page numbers, and the place of publication of the publisher. Okay, and we have a similar one here for books, which I'm not going to go through. And websites, all right? You do reference websites, and you put the date at which you actually looked at the website. Now, if you write a paper and you look at a website, you get some data out of it, or whatever you do, and then you put your paper down and you don't do anything for 6 months, do remember to at least go back to the website and check that what applied before applies now. So you put the date on. If a reference is in a language different from the language in which you're writing your paper, you say so. So here's an example, and it says, the final thing it says, in Chinese. That's what you do so that people know. Appendices. They're difficult to know whether you should or you shouldn't. But I've made this little table, or this little brain's gone, sorry. Anyway, will the reader need to know this? If the answer is no, and what I mean by need to about this information, it means, can they understand the paper without this information? If they don't need to know it, don't include it in the paper at all. So the answer must be, the reader needs to know. Yes. Do they need it to follow the argument? If the answer is yes, then you have to put it in the main body of the paper. But if the answer is no, you put it in an appendix. You might want, even though it isn't needed to understand what the paper is saying, you might want to include a wider range of data than is needed to understand the argument. And if you refer to this data several times, then really it should be in the main body of the text. If you only refer to it once, and there's a large amount of it, you probably put it in an appendix. Diagrams, well, journals usually refer to them as figures. It's according to Wikipedia. Oh yes, sorry, I didn't put the date at which I consulted it on there. A diagram is a symbolic representation of information according to some visualization technique, but I guess you know that. A photograph might be called a diagram, and we include diagrams to make the text easier to understand. That's why we do it. It isn't because we like to see lots and lots of photos of where you did your field work. Yes, a few showing important points are fine, but not half a dozen views from the top of the hill. They should be prepared specifically for the information being illustrated. And there's increasing amounts of software available to help me do this, but I have to say, and this is because I'm an old git, as we say in English, I prefer to use what used to be called a draftsperson, or draftsman or draftswoman, and somebody who actually will sit down, they'll do it digitally, but they'll prepare the diagram for you. You may want to use diagrams from another publication. That's okay, but you have to get copyright permission, which is a real nuisance. It takes ages to get copyright permission, particularly if, as we all, is the case, we don't want to pay. I've done a paper recently, and it took months to get the permission from the publishers. It's even difficult to find out who owns a copyright. Diagrams need to be clear, large enough when published, so that the text on them can be read easily. And one that people often forget is ensure that the text on the diagram is in the same language as the text in the paper. And obey the rules of the publisher in terms of the format and the size of the file for your diagrams. Here's an example of a diagram. Diagrams should be simple. They should include a north arrow or grid coordinates so we know which way up it is. This one has got a north arrow on it. So no, it hasn't. It's got grid coordinates, okay, so that's all right. It's got a scale bar, use simple patterns or colours, and include an explanatory caption. There's one on that one. And location maps should also include an inset showing the country in which your area falls and whereabouts. So that's just some general rules. And then when you've finished, you need to check a whole range of things. Completeness. I had somebody recently who sent me a paper with no references. It wasn't complete. They were very apologetic, and of course I allowed them to resubmit. But, you know, they were in a rush and they forgot. Accuracy, layout, spelling, oh, and please, spell checkers are not infallible. They don't know what you actually mean, so read the damn paper to find out. Check your grammar. Numbering. People miss out numbers. In other words, you get figure 1, 2, 3, 7, 8, 9, 10. Illustrations. Copyright. And if your paper is fine in respect of all the above, read it again. Yes, the moment you stop keying in stuff into your paper is not the end. You need to read it and reread it and reread it. Okay, I'm nearly finished, but this isn't the last slide. Here again are some references which relate to this presentation. Again, they are on the IAEG website, this presentation, so you don't need to write them down. But here, if you want to know the summing up of all the above, KISS. Just remember KISS. Keep it short and simple. Thank you.
I'm from a consultancy called Golden New Zealand. I have a question for you. In your role as editor, what would you say the top maybe 2 or 3 reasons are that you're refusing? What are the things you're seeing time and time again that you would suggest you know about?
It's a really good question. This isn't a fact that I normally put out, but I personally, that's me, not a member of my editorial board, not a reviewer, me, I reject half of all the papers received, okay? Half. Why? Well, various reasons. The simple reason is, let's say the English is too poor. I have to send ultimately the paper to a reviewer who may not have English as their first language. And if I struggle to understand it, my reviewers will definitely not understand it and the paper is rejected, but I provide them with help as to what to do about it. The next reason for rejection is that the paper is not, and remember I edit an international journal, the paper is not really very interesting in the sense that it doesn't bring anything new. It's merely a repeat of what other people have done, and we don't put that. I know those things, and it's a fine line, and it's judgment, but I'm the editor, and it's my judgment. I have to decide on these things, but if it's a repetition of something that's been done before, the paper will be rejected. But the main reason that papers are rejected is because they are not relevant to the journal to which they are submitted. Now, can I give some examples? Yes. I remember the Bulletin of Engineering Geology and the Environment. So you probably would work out that this is a journal for papers about engineering geology. So, and that needs defining, but that's it. So why would somebody send me a paper, as has happened, about growing some particular crop in some particular country and how they irrigated it and how the crop yields varied depending on how they watered it. I mean, it happens. More closer to the title, I do reject quite a number of papers which you may describe as geotechnical. I mean, to me, geotechnical engineering and engineering geology are not the same thing. They overlap, there's no doubt about that. But I have a simple rule for papers like that. If it has no geology in it, and many of these papers, these geotechnical engineering papers, do not have any geology in them. And I'm sorry, putting the word granite in and telling me they've done all these tests on granite does not pass the test of has it got any geology. So it's usually that papers either have no geology or no engineering geology. I have to draw that distinction because I get quite a number of papers from researchers, hydrocarbon researchers, who are talking about deep basins which might be reservoirs, and they go into the geology in great detail, but it's not engineering geology. So those are the main reasons. So the lesson is, make sure that the journal to which you send your paper is relevant to the subject of your paper. And it's no good trying to be clever and say, well, you know, I've published in that one, and I fancy that one. If your paper isn't relevant, don't send it.
Thank you for your meticulous presentation. I have a question. I wonder whether it is acceptable for me to cite some sentences from Wikipedia. Because, you know, when I come from some new terms, I usually go to the Wikipedia to get some news.
No, don't. I'll tell you why. Don't. It's all right for you to look at Wikipedia, but don't quote anything from Wikipedia, please, because there are lots of things in Wikipedia that are not true. All right? They're just not true. And if you're looking in Wikipedia because you don't know something, you're in no position to know whether what is written is actually correct. So my advice is not to use Wikipedia.
Being the student of science, I realize now that once I've applied for the PhD, and from Norway I got a letter that your experience is wonderful, but you are lacking in the research papers. Now I realize that we have done, every day we do lots of works in scientific field, like we prepare the drilling logs, storage logs, or landslide study. But the main thing is we are lacking the research papers. And I think your today's presentation will be the milestone in future. And thank you so much for that, sir.
I'd like to ask you one question. How do you rate the publications of the Nepal Geological Society today, and do you have any comments on them? I find a lot of grammatical errors and misspellings and this and that. I think we should take even more care on that. What do you think?
Most, I won't say all, but most journals or geological society publications should be, many are, proofread. Okay? What does proofreading mean? It means that somebody whose first language is the same as the language of the paper has read the paper with a view to ensuring that it is correctly written. I mean, I edit the bulletin, and Springer, the publisher, they employ proofreaders to read the papers. And when the proofreaders receive the papers, they are not necessarily very good from the point of view of their English or their French. But the proofreaders make them, okay. But something that I was told decades ago, when I first started getting involved with editing, was if you get 6 people to read a paper with a view to removing all the errors, you will remove 95% of them, not 100%. It's quite difficult to get that far.
Any other questions? I don't see any hand raised. In that case, I would like to thank Dr. Martin again for your excellent presentations.
Now it's a time to appreciate our team, what he did. Actually, this is really a very good time that we have a perfect lecture from Professor Martin Schussler. And we have this journal, Bulletin of Engineering Geology and the Environment. All of you are very much welcome to submit here. And the suggestions from reviewer and sometimes suggestions from editors are very useful to revise your paper, and we can publish it very easily. Okay, in that sense, thank you very much for this all, and I would like to give you one appreciation, token of appreciation to Professor Martin. And I have to appreciate our chair and co-chair also. Okay, Ganesh, please. And we have Rama Mohan, please. Okay, with this, we are now concluding our session. Tomorrow morning at 9 o'clock, we'll start our keynote lecture. Don't miss it. We have a perfect keynote lecture from Professor Pawan and Professor Hasegawa and our very good friend from Dr. Janas from Italy. Okay? Thank you very much and bye-bye.